Tonight, as you get ready for sleep, we'll explore one of modern science's most intriguing questions: why in such a vast universe we still haven't found evidence of other civilizations. We will calmly and methodically analyse the main theories that attempt to explain the Great Silence, from the biological and technological barriers that might prevent intelligent life from emerging, to the immense distances that separate us from other stars. Allow your mind to relax to the sound of these logical explanations, gently absorbing the knowledge, while your body finds the deep rest it deserves. There is no need to strain to understand. Simply let the information flow smoothly, guiding you toward a peaceful sleep filled with new perspectives on our place in the cosmos. Have you ever looked up at the night sky and wondered why, in a universe so vast and ancient, we haven't detected any signs of alien civilizations yet? This question forms the heart of what we call the Fermi paradox, named after physicist Enrico Fermi, who, during a lunch conversation in 1950, simply asked, "Where is everybody?" The paradox emerges from a seemingly straightforward calculation. Our Milky Way galaxy contains between 200 billion and 400 billion stars. Many of these stars have planets orbiting them. Current estimates suggest there could be billions of Earth-like planets in our galaxy alone. The universe is also incredibly old, about 13.8 billion years, while Earth has only existed for about 4.5 billion years. Given these numbers, countless civilizations should have had time to develop, expand, and spread throughout the galaxy long before humans even evolved. The math behind the Fermi paradox was formalized by astronomer Frank Drake in 1961 with his famous equation that attempts to estimate the number of detectable civilizations in our galaxy. Even with conservative estimates plugged into this equation, the result typically suggests that we should have detected evidence of extraterrestrial intelligence by now. Our Sun is relatively young compared to many stars in this galaxy. If just one technological civilization had emerged in our galaxy a few million years before us, a mere blink in cosmic timeframes, they could have potentially colonized or at least explored the entire Milky Way by now. The fact that we see no evidence of such exploration or colonization creates the paradox. Several factors make this absence of evidence particularly puzzling. Radio waves, which we've been broadcasting for over a century, travel at the speed of light. Any civilization within 100 light years would have had the opportunity to detect our presence if they possessed technology similar to our own. Furthermore, if an advanced civilization wanted to make their presence known, they could have placed obvious artificial structures or beacons that would be hard to miss. What makes the Fermi paradox so intriguing is that it forces us to examine our fundamental assumptions about life, intelligence, and technological civilization in the universe. Perhaps the evolution of intelligence is extraordinarily rare, or maybe the leap from intelligence to technology is an unusual development. It's possible that technological civilizations tend to have short lifespans, destroying themselves before achieving interstellar capabilities. This leads us to some rather unsettling possibilities. Perhaps technological civilizations invariably destroy themselves through nuclear war, climate change, artificial intelligence gone wrong, or some other technological disaster we haven't yet encountered. If this is true, it suggests that technological development might contain inherent dangers that few, if any, civilizations survive. This interpretation of the paradox serves as a warning about our own future. Another possibility is that advanced civilizations choose to remain silent and hidden. They might observe primitive civilizations like ours from a distance, similar to how we might observe wildlife without interfering. Or perhaps they communicate using technologies we haven't discovered yet, making their conversations invisible to our current detection methods. Some scientists have proposed that we might be among the first technological civilizations to emerge in our galaxy. While this seems statistically unlikely given the age of the universe, it cannot be ruled out. Perhaps some relatively recent event, like a gamma-ray burst that sterilized large portions of the galaxy, reset the evolutionary clock, and we're among the first to evolve since then. The implications of the Fermi paradox extend beyond astronomy, and touch on fundamental questions about our future. If we eventually detect evidence of extraterrestrial intelligence, it would suggest that civilizations can endure their technological adolescence and perhaps thrive for millennia or millions of years. This would be an optimistic sign for humanity's prospects. Conversely, if we continue to find silence despite increasingly sophisticated search methods, it might suggest that some great challenge lies ahead for technological species like our own. The paradox also influences how we think about space exploration and our potential expansion beyond Earth. If interstellar travel is simply too difficult or energy intensive for any civilization to achieve on a large scale, perhaps we should adjust our long-term expectations for human expansion into space. Alternatively, if the silence results from self-destruction, we should focus on addressing existential risks like nuclear weapons, climate change, and emerging technologies. When considering the Fermi paradox, we should remember that our search for extraterrestrial intelligence is still in its infancy. We've only been listening for radio signals for about 60 years, and we've only examined a tiny fraction of the sky across a limited range of frequencies. Our ability to detect biosignatures in exoplanet atmospheres is just beginning to develop. It's entirely possible that evidence of alien life or intelligence is waiting to be discovered just beyond our current technological reach. The Fermi paradox reminds us of how little we truly know about our place in the cosmos. While we have made remarkable progress in understanding the physics of our universe, we still know almost nothing about the prevalence of life beyond Earth or the typical evolutionary trajectory of technological civilizations. The answer to "where is everybody?" might reveal fundamental insights about our own future and the nature of intelligent life itself. As we continue to search the skies and develop new technologies to detect signs of life and intelligence beyond Earth, the Fermi paradox serves as a humbling reminder of the vast unknown that surrounds us. Whether we are alone among the first or simply haven't detected our galactic neighbours, yet remains one of the most profound unanswered questions in science. The resolution of this paradox, whenever it comes, will fundamentally change our understanding of our place in the universe. The Great Filter Theory. Imagine learning that countless civilizations across our galaxy had flourished and then vanished without a trace. Or worse yet, discovering that no other civilization has ever reached our current technological level. This is the essence of the Great Filter Theory, one of the most compelling potential explanations for the Fermi paradox, and perhaps the most unsettling. The Great Filter Theory was first proposed by economist Robin Hanson in 1998. It suggests that somewhere along the path from non-living matter to spacefaring civilization, there exists an extremely difficult barrier, a filter that prevents or drastically limits the emergence of advanced extraterrestrial civilizations. This would explain why we haven't detected signs of intelligent life, despite the vast number of potentially habitable planets in our galaxy. What makes this theory particularly intriguing is the question of whether this filter lies in our past or our future. If it's in our past, it means humanity has already successfully navigated the most difficult hurdle that prevents life from becoming intelligent and technological. This would be relatively good news for us, though it would suggest we might be alone or nearly alone in the galaxy. If the filter lies in our future, however, it suggests that virtually all technological civilizations encounter some catastrophe that prevents them from expanding into the cosmos, a prospect that doesn't bode well for humanity's long-term survival. The path from simple chemistry to spacefaring civilization involves many steps. Life had to originate from non-living matter, simple cells had to evolve into complex ones, multicellular organisms had to develop, intelligence had to emerge, and finally, technological civilization had to arise. Each of these transitions could potentially be the Great Filter. The origin of life itself, abiogenesis, might be extraordinarily rare. While we know that organic molecules are common throughout space, the jump from these building blocks to self-replicating life forms may require such specific conditions that it happens very infrequently. If this is the Great Filter, we've already passed it, which would be encouraging for our future, but would suggest that we're likely alone in our cosmic neighbourhood. Another candidate for the filter is the evolution of complex cells. On Earth, simple prokaryotic cells existed for nearly 2 billion years before eukaryotic cells with complex internal structures emerged. This transition apparently happened only once in Earth's history, suggesting it might be extremely improbable. If this is the case, we've again already passed through the filter. Intelligence itself could be the filter. While many species on Earth show remarkable cognitive abilities, only humans have developed advanced technology. Perhaps the evolution of human-level intelligence requires such a specific set of evolutionary pressures and circumstances that it rarely occurs, even on planets teeming with life. The most concerning possibility is that the Great Filter lies ahead of us. Perhaps nearly all technological civilizations destroy themselves shortly after developing advanced technology. Nuclear weapons, artificial intelligence, engineered pandemics, climate change, or technologies we haven't yet developed might typically lead to extinction before a species can become interstellar. If this is the case, our failure to detect alien civilizations becomes a dire warning rather than a curiosity. Resource depletion provides another potential future filter. Perhaps civilizations typically consume their available resources too rapidly to develop sustainable interstellar travel capabilities. Once they've exhausted what their home planet provides, they find themselves unable to make the leap to harvesting resources from space on a scale necessary for interstellar expansion. Interstellar travel itself might be the filter. While it doesn't violate any known laws of physics, the practical challenges of travelling between stars might be so immense that virtually no civilization overcomes them. The vast distances, the energy requirements, the timescales involved, and the technological challenges might combine to create a barrier that civilizations rarely if ever cross. The implications of the Great Filter theory are profound for how we think about humanity's future. If we've already passed the filter, we might be justified in feeling a certain cosmic responsibility as potentially one of the few intelligent species in our galaxy. If the filter lies ahead, understanding what it might be becomes critically important for our survival. Interestingly, our search for life elsewhere in the solar system and beyond could provide clues about the nature of the Great Filter. If we discover evidence of simple life on Mars or Europa, but this life never evolved beyond basic forms despite having billions of years to do so, it might suggest that the evolution of complex life is the filter. This would be relatively good news for us since we've already passed that stage. On the other hand, if we find evidence that complex life or even past civilizations were relatively common but all died out, it would strongly suggest that the filter lies in our future, a much more worrying prospect. This is why some scientists have joked that finding life on Mars would be bad news for humanity's prospects. As counterintuitive as that seems, the Great Filter theory has practical implications for our priorities as a civilization. If existential risks like nuclear war, climate change, or unaligned artificial intelligence constitute the filter that most civilizations fail to navigate, then addressing these risks should be among our highest priorities. Similarly, if the filter is related to resource depletion or the challenges of interstellar travel, investing in sustainable development and advanced space technology becomes crucial. What makes the Great Filter theory so compelling is that it provides a framework for thinking about humanity's place in the cosmos that aligns with both our current observations, the apparent absence of other civilizations, and our understanding of evolutionary and technological development. Unlike some explanations for the Fermi paradox that rely on speculative physics or alien psychology, the Great Filter requires only that some step in the development of interstellar civilizations be extraordinarily difficult. As we continue to search for signs of life beyond Earth and develop new technologies, we're essentially gathering data that will help us better understand where the Great Filter might lie. Every exoplanet we study, every sample we analyse from Mars or the moons of gas giants, and every radio signal we detect or fail to detect provides another data point. The Great Filter theory reminds us that our existence as a technological species may be far more precarious than we typically assume. It encourages us to take a longer view of our development and to carefully consider the potential consequences of our technological choices. Whether the greatest challenges to our existence lie behind us or before us remains unknown, but the answer to this question may be the most important discovery humanity ever makes. The Great Filter theory offers a sobering perspective on our cosmic uniqueness, but it's not the only framework that might explain our apparent solitude in the universe. Related to this concept is the rare Earth hypothesis, which suggests that while simple life might be common throughout the cosmos, the specific conditions needed for complex life are exceedingly uncommon. Developed in detail by geologist Peter Ward and astronomer Donald Brownlee in their book published in the year 2000, the rare Earth hypothesis proposes that the emergence of complex life requires a perfect storm of astronomical, geological, and biological factors that rarely align. According to this view, Earth is not just special, it's extraordinarily exceptional. At the heart of this hypothesis is the concept of the habitable zone, sometimes called the Goldilocks zone, where a planet orbits at just the right distance from its star for liquid water to exist on its surface. But the rare Earth hypothesis goes much further, suggesting that a truly life-friendly planet needs many more specific characteristics beyond just being in the habitable zone. For starters, we need to consider our Sun. It's a remarkably stable star with relatively low variability and the right spectrum of light to support photosynthesis, without delivering too much harmful radiation. Many stars in our galaxy are either too volatile, emit too much dangerous radiation, or don't provide the right kind of light for complex life to flourish. Additionally, our Sun is located in what some astronomers call the galactic habitable zone, not too close to the dangerous radiation near the galactic centre, but not so far out that there wouldn't be enough heavy elements to form rocky planets. The Earth's size and composition are also remarkably well suited for life. It's large enough to retain a substantial atmosphere, but not so massive that it would have become a gas giant. It contains the right balance of elements, including those needed for a magnetic field that shields us from solar radiation. This magnetic protection is crucial. Mars, for example, lost much of its atmosphere when its magnetic field faded, rendering its surface hostile to life as we know it. Perhaps one of Earth's most special features is our unusually large moon, formed by a chance collision with a Mars-sized body early in Earth's history. This oversized satellite stabilizes Earth's axial tilt, preventing the wild swings in climate that would occur if our planet wobbled chaotically on its axis. The stable seasons provided by this arrangement have given complex life forms time to adapt, rather than facing extinction through extreme climate variations. Another crucial factor is our planet's plate tectonics, the slow movement of Earth's crustal plates. This geological process recycles carbon, regulates atmospheric composition, and helps maintain a relatively stable climate over billions of years. Plate tectonics also creates diverse environments, from mountains to deep ocean trenches, providing numerous evolutionary niches for life to fill. This system appears to be relatively rare. Venus, similar to Earth in size and composition, lacks active plate tectonics and has become a hellishly hot world incapable of supporting life as we know it. The rare Earth hypothesis also considers Jupiter's role in our solar system. This massive gas giant acts as a sort of cosmic shield, its enormous gravitational field deflecting many comets and asteroids that might otherwise bombard Earth with life-extinguishing impacts. Without Jupiter's protective influence, Earth might have experienced far more frequent extinction-level impacts, potentially preventing complex life from gaining a foothold. Our solar system's relatively circular orbits are another fortunate characteristic. Many exoplanetary systems discovered so far have planets with highly elliptical orbits, which would create extreme seasonal variations that would challenge the development of complex life. Even the relatively low amount of dust and debris in our solar system compared to many others may have helped life evolve by reducing extinction events caused by impacts. Earth's water content hits a perfect balance, enough to create oceans, but not so much that the entire planet is covered in water without any land mass. This balance of land and water creates diverse habitats and enables the chemical cyclotheriling essential for complex life. Too much water and we might have ended up with a water world where land-based technological civilizations could never emerge. Too little and complex life might never have evolved at all. The timing of Earth's formation in the history of the universe also matters. If Earth had formed much earlier, there wouldn't have been enough heavy elements from previous generations of stars to create a rocky planet with the necessary chemical ingredients for life. If formed much later, increased radiation from nearby supernovae might have made complex life more difficult to sustain. Critics of the rare Earth hypothesis point out that we're working with a sample size of 1. Earth is the only planet we know of with complex life. They argue that we might be underestimating the adaptability of life and the variety of conditions under which intelligence could evolve. As we discover more exoplanets and develop better methods to analyse their atmospheres and surface conditions, we'll gain a clearer picture of how common or rare Earth-like planets truly are. However, proponents counter that each of the factors mentioned above represents a filter that reduces the probability of complex life emerging. When combined, these filters might reduce the number of truly Earth-like planets to a vanishingly small number, potentially explaining why we haven't detected signs of other technological civilizations. The implications of the rare Earth hypothesis are significant. If it's correct, it suggests that while microbial life might be relatively common in the universe, complex multicellular organisms would be rare, and technological civilizations rarer still. This would explain our apparent solitude without invoking future catastrophes as the Great Filter theory often does. It would mean that we've already won a kind of cosmic lottery by existing at all, making our planet and the life it supports all the more precious. As our instruments and techniques for studying exoplanets improve, we'll be able to test aspects of the rare Earth hypothesis. The discovery of numerous truly Earth-like planets with similar geological and astronomical characteristics would challenge the hypothesis, while finding that such worlds are indeed extremely uncommon would support it. Until then, the rare Earth hypothesis remains a compelling framework for understanding why, in a galaxy of hundreds of billions of stars, we've yet to detect signs of our cosmic neighbours. Even if complex life and technological civilizations do exist elsewhere in the universe. There's another significant challenge to consider: the barriers to communication between civilizations. These barriers might explain why, even if we're not alone, we haven't managed to detect or communicate with other intelligent species. The most fundamental barrier is simply distance. Our galaxy is approximately 100,000 light-years across. This means that a signal sent from one side of the galaxy would take 100,000 years to reach the other side. Even our closest stellar neighbour, Proxima Centauri, is over 4 light-years away. This creates not just a communication delay, but a practically insurmountable obstacle to any kind of meaningful conversation. Imagine asking a question and waiting 8 years for a reply, 4 years for your message to arrive, and 4 years for their response to return. This makes dynamic communication nearly impossible. These vast distances don't just impede communication, they also create a temporal barrier. Civilizations may exist at different times, with one rising long after another has fallen. A technological civilization might last for just a few thousand years before collapsing or transforming into something unrecognizable. Given that the universe is 13.8 billion years old, the odds of two civilizations existing simultaneously within communication range of each other might be extremely small. We might be broadcasting signals into space that will only reach their destination long after our civilization has ceased to exist in its current form. Beyond these physical limitations, there are significant barriers related to the nature of communication itself. We tend to assume that alien civilizations would use radio waves or other electromagnetic signals to communicate, just as we do. However, advanced civilizations might use communication technologies we haven't even conceptualized yet. They might communicate through neutrinos, gravitational waves, or other means that we either can't detect or don't recognize as communication. It's like expecting an ancient civilization to pick up on Wi-Fi signals. They wouldn't have the technology or even the conceptual framework to recognize what they were sensing. Even if we detected signals from another civilization, we would face the enormous challenge of interpretation. Human languages are difficult enough to translate when they evolve from common ancestral languages on the same planet with shared biological and cultural contexts. Imagine trying to decipher a message from beings with completely different sensory systems, cognitive structures, and evolutionary histories. They might perceive reality in ways fundamentally different from how we do. Consider how difficult it would be for humans to communicate with octopuses, despite sharing a planet and evolutionary history. Octopuses are highly intelligent but process information in a radically different way than humans, with a more distributed nervous system. Aliens might be far more different from us than octopuses are. They might experience time differently, perhaps processing information at rates thousands of times faster or slower than we do. Their messages might seem like random noise to us, or be so slow that we don't recognize them as dynamic communication at all. Different biological foundations would create further barriers. Aliens might have evolved from radically different biochemistry and perceive different parts of the electromagnetic spectrum than we do. A species that evolved to communicate through polarized light, infrasound, or electrical fields would develop communication systems optimized for those media, potentially making their messages unrecognizable to us as intentional communication. Cultural and conceptual differences present perhaps the most subtle but profound barriers. Even if we could technically receive and decode alien messages, we might not share enough conceptual common ground to understand their meaning. Mathematics is often proposed as a universal language, but even mathematical communication requires shared concepts of what constitutes a symbol or a pattern. Our entire way of thinking is shaped by our evolutionary history, biology, and culture. Aliens would have entirely different reference points. The problem of establishing common context is particularly challenging. Human communication depends heavily on shared context. We understand each other because we share a vast background of common experiences and knowledge. With aliens, we would have no shared history, culture, biology, or environment to draw upon. Creating a framework for mutual understanding would be an enormous challenge, requiring creative approaches to establishing basic concepts that both species could recognize. There's also the possibility that advanced civilizations might choose not to communicate broadly. they might be primarily interested in communicating with civilizations at a similar or higher technological level, using advanced methods that would be undetectable to less developed civilizations like ours. They might see broadcasting their presence as naive or dangerous, preferring to observe rather than announce themselves. Timescales of civilizational development add another layer of difficulty. The period during which a civilization uses radio technology might be just a brief phase in its development. Perhaps advanced civilizations quickly move beyond electromagnetic communications to more efficient or secure methods. Our own civilization has only been broadcasting radio signals for about 100 years, a mere blink in cosmic time. If this pattern is common, the window for detecting radio signals from other civilizations might be extremely narrow. These communication barriers don't mean that contact is impossible, but they do suggest that it would be far more challenging than science fiction typically portrays. Overcoming these barriers would require extraordinary patience, creativity, and technological advancement. It would likely be a multi-generational project requiring sustained effort over centuries or even millennia. Despite these challenges, efforts like the search for extraterrestrial intelligence, SETI, remain valuable. Even if the odds of success are low, the potential discovery of another technological civilization would be so significant that it justifies the effort. Furthermore, the very act of thinking about how to communicate across such vast barriers pushes us to examine our own assumptions about communication, intelligence, and our place in the universe. Understanding the barriers to communication between civilizations naturally leads us to examine the specific technological efforts we've made to detect extraterrestrial intelligence. The Bureau for Extraterrestrial Intelligence, commonly known as SETI, represents humanity's most organized attempt to detect signals from alien civilizations. However, despite decades of searching, SETI has yet to detect any confirmed extraterrestrial transmissions. This lack of success isn't necessarily because there's no one out there. It may instead reflect the significant technological limitations of our search efforts. When SETI began in the 1960s, the focus was primarily on searching for radio signals, based on the reasonable assumption that radio waves represent an efficient way to communicate across interstellar distances. Radio waves travel at the speed of light, can carry substantial information, and pass relatively unimpeded through the interstellar medium and planetary atmospheres. However, our ability to detect such signals is constrained by numerous factors that dramatically limit the effectiveness of our search. Perhaps the most obvious limitation is the sheer vastness of space. Our galaxy alone contains hundreds of billions of stars, and we've only been able to conduct detailed observations of a tiny fraction of them. Even with our most powerful radio telescopes, we can only listen to a small portion of the sky at any given moment. The analogy often used is that we're trying to find a needle in a cosmic haystack while only being able to examine a handful of hay at a time. The electromagnetic spectrum presents another challenge. Radio waves encompass a wide range of frequencies, and we don't know which specific frequencies alien civilizations might use for communication. Early SETI efforts focused on the water hole, a relatively quiet band of the radio spectrum between the hydrogen line and the hydroxyl line, based on the idea that intelligent species might choose this range specifically because it's less cluttered by natural cosmic emissions. However, this represents just a tiny slice of the possible frequencies aliens might use. Even when focusing on specific frequency ranges, our observations are limited in both duration and sensitivity. Many SETI observations consist of relatively brief listening periods directed at specific stars. If an alien civilization transmits signals intermittently rather than continuously, we might easily miss them if we're not listening at the right time. Additionally, our receivers can only detect signals that serve a certain power threshold. A civilization transmitting weaker signals, or one located farther away, might remain undetectable despite our best efforts. The nature of the signals themselves presents yet another challenge. We typically look for narrow-band signals that stand out from natural background noise, as these would be clear indicators of technological origin. However, advanced civilizations might use spread-spectrum communications, quantum encryption, or other sophisticated methods that would make their signals appear indistinguishable from natural cosmic noise to our current technology. Time represents a particularly vexing limitation. Radio technology is extremely recent in human history. We've only been generating radio signals for about 140 years, and we've only been deliberately searching for extraterrestrial signals for about 60 years. In cosmic terms, this is an incredibly brief window. If alien civilizations typically use radio technology for similarly short periods before moving to more advanced communication methods, the chances of two civilizations using compatible technology simultaneously become vanishingly small. Funding constraints have also significantly limited SETI efforts. Unlike many other scientific fields, SETI has often struggled to secure consistent financial support, leading to interrupted search programs and limited technological development. The original NASA SETI program was cancelled by Congress after just 1 year of operation in 1993, forcing SETI to rely largely on private funding ever since. This has restricted the scope and continuity of search efforts, making it more likely that potential signals could be missed. Interference from human-generated radio signals presents an increasing challenge as our technology proliferates. Earth is surrounded by a growing bubble of radio transmissions that can make it difficult to distinguish potential extraterrestrial signals from our own technological noise. This problem is becoming more acute as satellite networks expand and more devices communicate wirelessly, creating a background of radio chatter that SETI receivers must filter through. Data processing limitations have historically constrained SETI as well. The amount of data generated by radio telescope observations is enormous, and analysing this data to identify potential signals of interest requires substantial computing power. While distributed computing projects like SETI at Home helped address this challenge by using volunteers' computers to process data, the computational requirements remain significant. Modern machine learning approaches are beginning to help with this problem, but they bring their own limitations and biases. Perhaps most fundamentally, SETI operates under certain assumptions about what alien technology might look like. We assume that aliens would use electromagnetic signals for communication, that they would generate distinct patterns distinguishable from natural phenomena, and that they would transmit in ways we could recognize as artificial. If these assumptions are incorrect, if advanced civilizations use communication technologies based on principles we haven't yet discovered, then our current SETI approaches would be like ancient Romans trying to detect television broadcasts. Despite these limitations, SETI continues to advance. New telescopes like the Square Kilometre Array will dramatically increase our observational capabilities. Improvements in computing power and artificial intelligence are enhancing our ability to analyse vast datasets and identify subtle patterns. The field is also expanding beyond traditional radio SETI to include optical SETI, looking for laser signals, searches for technosignatures like atmospheric pollutants or megastructures, and even attempts to detect artifacts within our own solar system. While the technological limitations of SETI are substantial, they're not insurmountable. Each new generation of technology expands our ability to search and increases the probability of detection if other technological civilizations exist. The absence of detected signals so far doesn't mean we're alone. It may simply reflect the preliminary nature of our search efforts compared to the enormous scale of the task. As our technology improves and our search methods diversify, we gradually improve our odds of making contact if there's anyone out there to contact. These technological limitations of SETI might explain why we haven't detected alien civilizations yet, but there's another possibility that's both more unsettling and potentially more profound. Maybe advanced civilizations are deliberately hiding. This concept, popularized in recent years as the dark forest theory, offers a chilling explanation for the cosmic silence we observe. The dark forest theory derives its name from a metaphor used in Liu Cixin's science fiction trilogy, The Three-Body Problem, where the universe is compared to a dark forest. In this forest, all civilizations are like armed hunters moving stealthily through the trees. They know others exist, but when they encounter one another, the safest action is to shoot first, as the alternative could mean their own destruction. In this scenario, silence and stealth become the optimal survival strategies. The core premise of the dark forest theory is that in a universe of limited resources, where the true intentions of other civilizations cannot be known with certainty, the rational behaviour for any technological civilization is to hide its existence. This stems from several key assumptions about the nature of interstellar relations. First, the theory assumes that all civilizations seek to survive and expand. Second, it assumes that resources, while vast, are ultimately finite in the universe. Third, and perhaps most crucially, it assumes that civilizations cannot know the true intentions of others they might encounter, creating a fundamental chain of suspicion that cannot be broken. Under these conditions, making contact with another civilization represents an existential risk. The The other civilization might be benevolent, but it might also see newcomers as potential future competitors for resources, or as potential threats to be eliminated before they grow more powerful. With no way to be certain of another civilization's intentions, and no ability to establish trust across interstellar distances, the safest approach is to remain hidden, and if discovered, to eliminate potential threats before they can do the same to you. This creates what game theorists would recognize as a grim version of the prisoner's dilemma extended to cosmic scale. While cooperation might benefit all parties in the long run, the inability to ensure mutual cooperation and the extreme stakes involved, potentially the survival of one's entire species, push rational actors toward non-cooperation and preemptive aggression. If the Dark Forest theory is correct, then advanced civilizations might take extraordinary measures to avoid detection. They would refrain from broadcasting radio signals into space. They might limit their electromagnetic emissions by using tight beam communications or technologies that don't leak detectable radiation. They could confine their activities to environments that naturally shield emissions, such as underground habitats or the far sides of moons. They might even deliberately avoid large-scale engineering projects that would create noticeable changes to their stellar neighbourhood. Some proponents of this theory suggest that truly advanced civilizations might take even more extreme measures, potentially sterilizing regions of space around them to eliminate any emerging technological civilizations before they can become potential competitors. In this grim scenario, the fact that Earth has been allowed to develop unhindered might simply indicate that no advanced civilization has yet detected our presence. From this perspective, humanity's active attempts to broadcast our location and details about our civilization, such as the Arecibo message sent in 1974 or the various physical plaques and recordings on our space probes, might be considered dangerously naive. By announcing our presence without knowing what's out there, we could be drawing unwanted attention from civilizations following Dark Forest principles. Critics of the Dark Forest theory point out several potential flaws in its reasoning. They argue that truly advanced civilizations would likely have access to resources far beyond what we can currently imagine, reducing competition pressures. They suggest that intelligence and cooperation often evolve together, making hostile advanced civilizations less likely. Some also point out that the vast distances between stars create natural barriers that would make direct conflict impractical regardless of intentions. Additionally, the theory assumes a certain level of homogeneity among alien motivations, that all or most would follow similar logic regarding survival and competition. This may be an anthropocentric view that projects human competitive instincts onto entities that might have evolved under entirely different selective pressures. Despite these criticisms, the Dark Forest theory has gained significant attention, because it offers a coherent explanation for the Fermi paradox that doesn't require alien civilizations to be rare or non-existent. Instead, they could be abundant but hidden, creating a universe that appears empty but is actually teeming with life that has learned the survival value of silence. If the Dark Forest theory has merit, it raises profound questions about humanity's approach to space exploration and our attempts at interstellar communication. Should we continue broadcasting our presence, hoping to connect with benevolent civilizations? Or should we adopt a more cautious approach, limiting our detectability until we better understand what might be out there? These questions highlight how theories about alien civilizations ultimately reflect back on our understanding of ourselves and our place in the cosmos. The implications extend beyond merely explaining our failure to detect alien signals. They suggest that as we continue to develop as a technological civilization, we may face difficult choices about how openly we announce our presence to the cosmos. In a dark forest, making noise might attract attention we're not prepared to handle. The Dark Forest theory presents a sobering view of interstellar relations, but there's another explanation for our cosmic loneliness that is perhaps even more radical. Maybe our entire universe isn't what we think it is. This brings us to the simulation theory, which proposes that what we experience as reality, including all the stars, galaxies, and potential alien civilizations, might actually be an incredibly sophisticated computer simulation. While this might sound like science fiction, the concept has been seriously explored by philosophers, physicists, and computer scientists. The most famous formulation comes from philosopher Nick Bostrom, who published a paper in 2003 arguing that at least one of three propositions must be true. Either advanced civilizations typically go extinct before developing simulation technology, or they have no interest in running simulations of their evolutionary past. or we are almost certainly living in a simulation. The logic behind this argument is straightforward. If it's possible for civilizations to develop technology capable of creating fully immersive, detailed simulations of conscious beings, including entire universes for those beings to inhabit, then the number of simulated minds could vastly outnumber real minds. Statistically speaking, any randomly selected mind, including yours and mine, would more likely be a simulated one than a biological one in the original base reality. If we accept the possibility that we might be living in a simulation, this has fascinating implications for the Fermi paradox. The apparent absence of alien civilizations could be explained not by their actual absence, but by the parameters set by whoever or whatever created our simulation. The lack of aliens might be a deliberate design choice, a processing limitation, or simply an aspect of the simulation that hasn't been fully implemented yet. From this perspective, the search for extraterrestrial intelligence takes on a different character. We might be looking for something that doesn't exist in our simulated reality, even if it exists in the base reality outside our simulation. Alternatively, the discovery of alien life might be programmed to occur at a specific point in our simulated development, perhaps when we reach a certain technological threshold or solve particular scientific problems. The simulation hypothesis also offers explanations for other cosmic puzzles. The apparent fine-tuning of physical constants that make our universe suitable for life, often cited as evidence for either multiple universes or intelligent design, could simply reflect the parameters chosen by the simulators to create an interesting or habitable environment. The seemingly arbitrary speed limit of the universe, the speed of light, might function as a processing limitation, preventing simulated beings from travelling too quickly and requiring more computational resources than available. Critics of the simulation theory point out that it's essentially unfalsifiable. We can't test whether we're in a simulation because any experiment we design would itself be part of the simulation. Others argue that creating a simulation with the level of detail we observe in our universe would require computational resources so vast that even advanced civilizations might find it impractical. However, proponents counter that a simulation wouldn't need to render every subatomic particle in the universe at all times. Only the parts being observed would need full detail, similar to how video games render only what the player can see. If we are in a simulation, the implications for our search for extraterrestrial life are profound. Perhaps aliens don't appear in our observations because they haven't been programmed into our particular simulation. Maybe the purpose of our simulation is specifically to study how an intelligent species, humans, responds to apparent cosmic loneliness. Or perhaps alien civilizations are part of the simulation but are programmed to remain hidden until humans reach a certain developmental milestone. The simulation hypothesis connects to earlier theories we've discussed. The Great Filter might not be a natural phenomenon, but a programmed feature of our simulation. The rare Earth conditions might be parameter settings chosen by the simulators. The dark forest scenario might be a programmed behavioural pattern, rather than a natural evolutionary outcome. Each of these could be elements of the simulation's design, rather than fundamental truths about reality. Some scientists have proposed potential ways to test whether we're living in a simulation. These include looking for glitches or patterns in the cosmic microwave background radiation, searching for evidence of computational shortcuts in physics, or identifying limits to quantum computation that might indicate underlying processing constraints. However, a sufficiently advanced simulation would presumably be designed to prevent such detection methods from succeeding. For those troubled by the simulation hypothesis, there's some comfort in the idea that even if our universe is simulated, our experiences and consciousness remain real to us. The joy, pain, curiosity, and wonder we feel are no less meaningful if they arise from complex information processing rather than biological processes. Our search for understanding and connection across the cosmos would still represent something genuine about our nature, simulated or not. The simulation hypothesis also raises intriguing questions about the nature and the motivations of the hypothetical simulators. Are they scientists studying evolutionary patterns? Game designers creating an elaborate reality for entertainment? Or perhaps our distant descendants running ancestral simulations to better understand their history? Each possibility suggests different implications for whether aliens would be included in the simulation and how they might interact with us. If our universe is indeed a simulation designed with specific parameters, the absence of detectable alien civilizations might not be a mystery at all, but rather a feature of the program. Perhaps our simulated universe is deliberately designed as a single-player experience, focusing computational resources on Earth and humanity, while rendering the rest of the cosmos as a vast but ultimately empty backdrop. Or maybe the simulation has a narrative structure, with aliens programmed to appear at a specific point in humanity's development, creating a cosmic first contact scenario precisely when the simulators decide the time is right. While the simulation hypothesis offers a thought-provoking explanation for the Fermi paradox, it ultimately leads us back to questions about our own place in the universe and the nature of consciousness itself, whether we exist in base reality or a simulated one. Our drive to understand our cosmic context reflects something fundamental about human nature and our relationship with the unknown. This discussion of the simulation theory highlights an important factor that influences all our thinking about extraterrestrial life: our tendency to view the cosmos through a distinctly human lens. This anthropocentric bias, the inclination to project human characteristics, motivations, and limitations onto non-human entities, profoundly shapes our search for alien life, potentially blinding us to forms of life and intelligence that don't match our expectations. From the beginning, our search for extraterrestrial intelligence has been guided by assumptions rooted in human experience. We look for planets with liquid water because all life on Earth requires it. We search for oxygen in alien atmospheres because it's essential to human survival. We scan for radio signals because that's a technology humans developed. At every step, we use ourselves as the template for what alien life might be like. This makes practical sense. We have only one example of a life-bearing planet, and one example of an intelligent species that has developed technology. Working from what we know is a reasonable starting point. However, this approach may severely limit our ability to recognize alien life if it differs significantly from terrestrial patterns. Consider how we define a habitable planet. The traditional habitable zone is defined as the region around a star where liquid water could exist on a planet's surface. This definition is based entirely on the temperature range suitable for Earth-like carbon-based, water-dependent life. But what if alien life uses a different solvent than water? Ammonia remains liquid at much lower temperatures than water, while formamide remains liquid over a wider temperature range. Life based on these solvents might thrive on planets we would consider too cold or otherwise unsuitable. Our bias extends to the chemical basis of life itself. We focus on carbon-based life because all Earth life uses carbon as its fundamental building block. Carbon forms complex, stable molecules and can create the variety of structures needed for life as we know it. However, silicon shares many chemical properties with carbon, and could theoretically form the basis for alien biochemistry, particularly in environments very different from Earth. By focusing exclusively on carbon-based chemistry, we might miss signs of silicon-based life or other exotic biochemistries. The definition of intelligence itself reflects our anthropocentric perspective. We tend to equate intelligence with tool use, technological development, and symbolic communication, all characteristics that humans excel at and that have driven our species' success. But intelligence could manifest in completely different ways. On Earth, octopuses display remarkable problem-solving abilities despite having a nervous system radically different from our centralized brain. Alien intelligence might be distributed across a collective rather than housed in individual organisms, more like a beehive mind than a human one. Our search for technological signatures is perhaps the area most influenced by anthropocentric thinking. We look for radio transmissions because humans discovered radio technology early in our technological development. We search for artificial structures that would be visible to our telescopes because those are the kinds of large-scale projects humans might build if we had more advanced technology. But an alien civilization might develop along an entirely different technological pathway, creating technologies that don't emit radio waves or build large structures. Even our conceptions of what motivates intelligent life reflect human biases. We assume aliens would be curious about other life forms and eager to communicate because humans generally exhibit these traits. We imagine they would expand and colonize because human societies have historically been driven to explore and settle new territories. These assumptions might not apply to intelligences that evolved under different evolutionary pressures or with different cognitive architectures. Timescales represent another area where anthropocentric bias limits our thinking. Human civilization has existed for a few thousand years, and our technological civilization for only a few hundred. We tend to think in terms of human lifespans and human historical timeframes, but alien life might operate on vastly different timescales. perhaps communicating so slowly that a single message might take centuries to complete, or so quickly that their entire civilization rises and falls in what would be a brief moment to us. Such differences would make mutual recognition, let alone communication, extremely challenging. Our sensory biases also influence how we search for life. Humans are visual creatures, with vision as our dominant sense. We design our detection methods around what we can see or visualize: visible light astronomy, infrared signatures, visual inspection of terrain. But alien life might primarily sense the world through means we consider secondary or don't possess at all: electrical fields, polarized light, or sensory modalities we haven't even imagined. The language we use to discuss alien life reveals our anthropocentric frame of reference. We talk about intelligence, communication, technology, and civilization, all concepts defined by human experience and achievement. This terminology may be inadequate for describing truly alien forms of existence and organization that don't map neatly onto human categories. Recognizing our anthropocentric bias doesn't mean abandoning our search methods entirely. Starting with what we know, life on Earth, is a practical approach given our limited resources. However, acknowledging this bias should encourage us to broaden our search parameters, consider alternative signatures of life and intelligence, and remain open to discoveries that don't fit our preconceptions. Some astrobiologists are working to overcome these biases by developing agnostic biosignature frameworks, approaches that look for any significant chemical disequilibrium or complexity that can't be explained by non-biological processes, rather than specifically Earth-like biosignatures. Similarly, SETI researchers are expanding beyond traditional radio searches to consider a wider range of potential technosignatures. Overcoming anthropocentric bias requires intellectual humility, acknowledging that our understanding of life, intelligence, and technology is based on a sample size of one, and that the universe may contain possibilities far beyond our current imagination. By expanding our conception of what life and intelligence might look like, we improve our chances of recognizing alien life if and when we encounter evidence of it. Recognizing our anthropocentric bias in the search for extraterrestrial life opens the door to considering alternative explanations for the apparent silence of the cosmos. One particularly intriguing theory that addresses our failure to detect alien civilizations despite the mathematical probability of their existence is the zoo hypothesis. This concept suggests that extraterrestrial civilizations are aware of Earth and human development, but have deliberately chosen not to make contact with us. First proposed by radio astronomer John Ball in 1973, the zoo hypothesis posits that Earth may be something like a wildlife preserve or zoo exhibit from the perspective of more advanced civilizations. According to this idea, advanced alien species might have established a policy of non-interference with developing planets like Earth, allowing us to evolve naturally without external influence or interference. This hypothesis addresses several aspects of the Fermi paradox in one elegant solution. It explains why we haven't detected signals from alien civilizations despite their potential abundance. They are deliberately keeping quiet in our vicinity. It explains why no one has visited Earth, or at least made their visits obvious. They're observing a hands-off policy, and it explains why we seem to have developed without any clear alien intervention. That's precisely the point of the arrangement. The zoo hypothesis assumes the existence of a galactic community or federation of some kind with established ethical protocols regarding contact with developing civilizations. This might sound like science fiction, but it's a logical extension of how humans already think about conservation and anthropological research. We establish nature preserves to protect endangered species from human interference. Anthropologists studying isolated human tribes often adopt minimal contact policies to avoid disrupting indigenous cultures. If humans can develop such ethics regarding non-interference, it seems reasonable that more advanced civilizations might apply similar principles on a cosmic scale. One version of the zoo hypothesis suggests that Earth might be under a kind of galactic quarantine until we reach a certain developmental threshold. This could be technological achievement, social development, or ethical maturity. Perhaps we need to demonstrate peaceful cooperation on a global scale, solve existential threats like climate change, or develop particular technologies that would enable us to participate in a wider galactic community. Until then, the hypothesis suggests, we're kept in isolation for our own protection and development. The zoo hypothesis connects well with reported phenomena like unidentified flying objects. If Earth is under observation, occasional monitoring missions or equipment malfunctions might explain rare sightings of unusual aerial phenomena without requiring full open contact. This aspect of the theory has made it popular in both scientific and public discourse about extraterrestrial intelligence. Testing the zoo hypothesis presents unique challenges. By its very nature, if advanced civilizations are deliberately hiding from us, direct evidence would be difficult or impossible to obtain. The hypothesis is essentially unfalsifiable in scientific terms. We can't prove that aliens aren't hiding from us. However, as our technology advances and our observational capabilities expand, continued failure to detect alien civilizations despite increasingly sophisticated search methods could be seen as circumstantial evidence supporting the zoo hypothesis. Some variations of the hypothesis suggest there might be leakage from the containment system. Perhaps some alien civilizations disagree with the non-interference policy and occasionally attempt contact. Or maybe the system isn't perfect and evidence occasionally slips through the cracks. Proponents suggest that this might explain anomalous observations or apparent patterns in certain reported encounters. Critics of the zoo hypothesis point out several weaknesses. First, it requires a galaxy-wide consensus among potentially thousands of different civilizations, each with their own ethics, motivations, and interests. Maintaining such a conspiracy of silence would be challenging enough among different human nations. Achieving it across different species with potentially radically different psychologies seems even more implausible. Second, it assumes that all advanced civilizations would share similar ethical views about non-interference, which may be projecting human ethics onto alien minds. Third, it doesn't explain why we don't observe alien activity elsewhere in the galaxy, outside the vicinity of Earth. Despite these criticisms, the zoo hypothesis remains one of the more compelling explanations for the Fermi paradox, because it doesn't require us to assume that intelligent life is rare. Instead, it suggests that the universe might be teeming with life and civilization. We just aren't allowed to see it yet. The hypothesis raises intriguing questions about what kind of development would qualify a species for admission to the galactic community. Would it be technological achievement, ethical development, environmental stewardship, peaceful coexistence? The answer might reveal something profound about the nature of sustainable technological civilization. If the zoo hypothesis is correct, it suggests that humanity's current situation is temporary. Eventually, we would reach whatever threshold is required for contact, and our understanding of the universe would dramatically expand overnight. The silent stars would suddenly reveal teeming civilizations that have been there all along, watching and waiting for us to join them. This perspective offers a hopeful view of both our future and the current state of the cosmos. We're not alone, we're just not ready yet. The flip side of this hopeful interpretation is more sobering. If advanced civilizations are deliberately hiding from us, it might be because technological development comes with significant risks. Perhaps they're waiting to see if we survive our own technological adolescence before making contact. Our current planetary challenges, nuclear weapons, climate change, emerging biotechnology risks, artificial intelligence safety, might represent the very tests we need to pass before the cosmic quarantine is lifted. Whether or not the zoo hypothesis accurately explains our apparent cosmic loneliness, it reminds us that the absence of evidence isn't necessarily evidence of absence when it comes to extraterrestrial intelligence. The silent universe we observe could reflect not emptiness, but a deliberate choice made by civilizations far more advanced than our own. The zoo hypothesis encourages us to look at our own development from a cosmic perspective, considering what kind of civilization we might become if given thousands or millions more years of development. It also raises the possibility that the search for extraterrestrial intelligence might ultimately succeed not through our efforts to detect them, but through their decision that we're finally ready for contact. Our discussions so far have focused primarily on technological civilizations that might be similar to humans in at least some basic ways. But what if life elsewhere in the universe differs from Earth life at the most fundamental level? This brings us to one of the most fascinating areas in astrobiology: the possibility of life beyond carbon-based biochemistry. All life on Earth shares the same basic biochemical foundation. We are carbon-based organisms that use water as a solvent for biological processes. Our DNA is built from the same nucleotide building blocks, and our proteins are assembled from the same 20 amino acids, with extremely rare exceptions. This uniformity reflects our common evolutionary origin. All life on Earth descends from a common ancestor that lived perhaps 3.8 billion years ago. But there's no reason to assume that life elsewhere in the universe would follow the same chemical pathways. In fact, even within the constraints of known chemistry and physics, scientists can envision several alternative biochemical foundations for life. Understanding these possibilities dramatically expands the range of environments where we might find alien organisms. Carbon earned its central role in Earth's biochemistry due to its remarkable chemical versatility. Carbon atoms can form stable bonds with up to 4 other atoms simultaneously and can link together in diverse arrangements including chains, rings, and complex 3-dimensional structures. This versatility allows for the incredible diversity of organic molecules that make up living organisms. Silicon, directly below carbon on the periodic table, shares some of carbon's chemical properties and has long been proposed as a potential alternative foundation for alien biochemistry. Like carbon, silicon can form bonds with up to 4 other atoms and can create chain structures. Silicon-based compounds called silanes are roughly analogous to hydrocarbons, though they're generally less stable in Earth conditions. A silicon-based organism might thrive in environments much hotter than those suitable for carbon-based life. As silicon-oxygen bonds, silicones, are more stable at high temperatures than the carbon-oxygen bonds in organic molecules. Silicon biochemistry might be well suited to planets closer to their stars than Earth is to our Sun, where surface temperatures would cook carbon-based organisms. Beyond the building blocks themselves, the solvent in which biochemistry occurs could also differ from Earth's water-based systems. Water has several properties that make it an excellent solvent for life. It remains liquid across a relatively wide temperature range, can dissolve many different compounds, participates in numerous chemical reactions, and has high heat capacity that helps stabilize temperatures. However, other liquids could potentially serve as biological solvents in different environmental conditions. Ammonia, for instance, shares many of water's useful properties and remains liquid at much lower temperatures, as cold as -78 degrees Celsius at Earth's atmospheric pressure. An ammonia-based biochemistry might thrive on the frigid worlds of the outer solar system or planets orbiting red dwarf stars at distances where water would be permanently frozen. Methane and ethane lakes on Saturn's moon Titan have sparked particular interest as potential habitats for exotic life. These hydrocarbon lakes remain liquid at the extremely cold surface temperature of -180 degrees Celsius. While any life in such environments would require fundamentally different biochemistry than Earth life, some scientists have proposed mechanisms by which methane could serve as a solvent for silicon or even carbon-based life adapted to extreme cold. Even more exotic possibilities exist. Sulfuric acid, which occurs naturally in the clouds of Venus, could potentially serve as a biological solvent. Liquid nitrogen, though extremely cold, has been theoretically proposed as another possibility. Some researchers have even speculated about life in environments where conventional liquids couldn't exist, such as the surfaces of neutron stars, where exotic forms of matter might support information processing structures analogous to biochemistry. Expanding our conception of possible biochemistries directly impacts where and how we search for life beyond Earth. If we limit ourselves to looking for carbon-based, water-dependent life, we might overlook thriving biospheres based on different chemical foundations. This realization has influenced recent shifts in astrobiology toward focusing on more general biosignatures rather than specifically Earth-like signs of life. For instance, rather than looking exclusively for oxygen in exoplanet atmospheres, a signature of Earth's plant life, astrobiologists now emphasize searching for any atmospheric gases that appear to be in chemical disequilibrium, a potential sign of biological processes regardless of their specific chemistry. Similarly, instead of focusing solely on the traditional habitable zone where liquid water could exist, researchers are considering a broader range of planetary environments that might support alternative biochemistries. Within our own solar system, several locations once considered inhospitable might host exotic life forms. Titan's hydrocarbon lakes could potentially support methane-based life. The subsurface ocean of Saturn's moon Enceladus, while water-based, contains chemicals that could provide energy for unconventional metabolic processes. Even the sulfuric acid clouds of Venus, with temperatures and pressures less extreme than the planet's surface, have been proposed as potential habitats for highly specialized organisms. The existence of extremophiles on Earth, organisms that thrive in conditions once thought incompatible with life, lends credibility to the possibility of truly alien biochemistries. We've discovered Earth organisms that live in near boiling acidic hot springs, in the crushing pressures of the deepest ocean trenches, in highly radioactive environments, and in rocks miles beneath the Earth's surface. While these extremophiles still use carbon-based, water-dependent biochemistry, they demonstrate that life can adapt to a far wider range of conditions than we once thought possible. The possibility of non-carbon-based life forms remains speculative but scientifically grounded. No fundamental law of physics or chemistry prohibits silicon-based life or organisms using ammonia or methane as solvents. The challenge lies in determining how likely such alternative biochemistries are to arise through natural processes, and how we might detect them if they exist. If such exotic life forms do exist elsewhere in the universe, they might be even more difficult to recognize than alien carbon-based life. Our scientific instruments and analytical techniques are optimized to detect familiar carbon compounds and metabolic processes. Truly alien biochemistry might register as mere geological processes to our current detection methods, or might be entirely invisible to them. Understanding the possibilities of alternative biochemistries isn't just relevant to our search for alien life. It also helps us understand the nature of life itself more fundamentally. By considering how life might function beyond the specific chemical pathways that evolved on Earth, we gain insight into which aspects of life are contingent accidents of our particular evolutionary history, and which might be universal features of any self-organizing, self-replicating system. The exploration of possible non-carbon-based life reminds us that our search for alien life must be guided by both imagination and scientific rigor. We need to expand our conception of what life might look like while developing practical methods to detect its presence. This balance between openness to truly alien possibilities and the constraints of practical scientific investigation represents one of the most fascinating challenges in our quest to understand whether we share our universe with other living beings. The exploration of alternative biochemistries broadens our understanding of what alien life might look like, but it also highlights another fundamental challenge in the search for extraterrestrial intelligence. Even if other technological civilizations exist, the immense difficulties of interstellar travel might prevent us from ever meeting them in person. The vast distances between stars present formidable barriers that make physical contact between civilizations an enormously challenging prospect. To appreciate the scale of this challenge, consider that the closest star system to our own, Alpha Centauri, lies approximately 4.3 light-years away. This means that light, the fastest thing in the universe, takes more than 4 years to travel between our solar system and our nearest stellar neighbour. To put this in perspective, if you could somehow travel at the speed of our fastest spacecraft, like NASA's Parker Solar Probe, which reaches speeds of about 400,000 miles per hour at its closest approach into the Sun, it would still take nearly 7,000 years to reach Alpha Centauri. These vast distances create what scientists call the tyranny of the rocket equation, a reference to the fundamental physics that makes interstellar travel so challenging. The rocket equation, developed by Russian scientist Konstantin Tsiolkovsky in the early 20th century, describes how the mass of propellant needed increases exponentially with the desired change in velocity. Simply put, to go faster you need more fuel, but carrying more fuel makes your spacecraft heavier, requiring even more fuel to accelerate that additional mass. This creates a vicious cycle that quickly becomes impractical for the extreme velocities needed for interstellar travel. Traditional chemical rockets, the kinds that took humans to the moon, are entirely inadequate for interstellar journeys. Even nuclear propulsion, which could theoretically provide much higher speeds, faces enormous engineering challenges. Project Orion, a concept studied by NASA in the 1960s, proposed using nuclear pulse propulsion, essentially a series of nuclear explosions behind a spacecraft, to reach speeds of up to 10% the speed of light. Even at this tremendous velocity, a journey to Alpha Centauri would still take over 40 years. More exotic propulsion concepts have been proposed, such as fusion rockets, antimatter engines, or beamed propulsion using powerful lasers to accelerate lightweight sails. The Breakthrough Starshot initiative, announced in 2016, aims to use ground-based lasers to accelerate gram-sized spacecraft to 20% the speed of light, potentially reaching Alpha Centauri in about 20 years. However, these technologies remain theoretical or in very early experimental stages and face enormous engineering hurdles. Beyond propulsion challenges, interstellar travelers would face numerous other hazards. The interstellar medium, while sparse, contains dust and gas particles that would impact a fast-moving spacecraft with tremendous energy. At just 10% the speed of light, a collision with a grain of sand would release energy equivalent to a large explosion. Shielding against these impacts adds mass to the spacecraft, exacerbating the propulsion problem. Radiation presents another serious hazard. Earth's magnetic field and atmosphere protect us from much of the cosmic radiation that permeates space. Travellers on an interstellar journey would be exposed to this radiation for decades or centuries, requiring heavy shielding or other protective measures that again add mass to the spacecraft. The timescales involved in interstellar travel create social and biological challenges as well. Even if we develop propulsion systems capable of reaching 10% the speed of light, far beyond our current capabilities, a journey to a star just 10 light-years away would still take a century. This means that any crewed interstellar mission would likely be a multi-generational endeavour, with children and grandchildren continuing the mission their ancestors began. Alternatively, some scientists have proposed technologies like suspended animation or human hibernation to allow travellers to survive long journeys in a dormant state. More speculatively, if mind uploading ever became possible, digital consciousness could potentially be sent on interstellar journeys without the need for biological bodies and their life support requirements. However, these approaches remain firmly in the realm of speculation rather than near-term technological possibilities. The enormous energy requirements for interstellar travel present another barrier. Accelerating even a relatively small spacecraft to a significant fraction of the speed of light would require energy equivalent to a large nation's entire annual energy production. While advanced civilizations might have access to vastly more energy than we do currently, perhaps through technologies like Dyson spheres that capture a significant portion of a star's energy output, the energy costs remain daunting. All these challenges apply not just to human interstellar travel, but to any technological civilization, regardless of their biology or specific technological path. The laws of physics that make interstellar travel so difficult are universal. This suggests that even if the galaxy contains many advanced civilizations, they might all be effectively isolated from one another by these fundamental physical constraints. This perspective provides another potential answer to the Fermi paradox. Perhaps interstellar travel is so extraordinarily difficult that it rarely or never occurs, even among civilizations far more advanced than our own. Civilizations might be common in the galaxy, but each remains confined to its home star system or perhaps a small neighbourhood of nearby stars, unable to expand further due to the practical limitations of physics. Some theorists have suggested that truly advanced civilizations might eventually develop technologies that circumvent these limitations, perhaps discovering ways to create stable wormholes, warp space-time, or exploit other exotic physics that would enable faster-than-light travel. However, our current understanding of physics suggests that such technologies might be fundamentally impossible rather than merely difficult. The speed of light appears to be a genuine cosmic speed limit, not simply an engineering challenge to overcome. If interstellar travel proves prohibitively difficult for biological beings, perhaps contact between civilizations will occur primarily through electromagnetic signals or robotic probes. Radio waves, light, and other forms of electromagnetic radiation travel at the speed of light, still slow on a galactic scale, but much faster than any physical spacecraft we can currently envision. A conversation conducted via radio signals between Earth and a civilization 10 light-years away would involve 20-year delays between questions and answers, slow by human standards, but potentially manageable for patient civilizations. The challenges of interstellar travel have important implications for how we think about first contact scenarios. If physical meetings between civilizations are extraordinarily rare, then protocols for handling such encounters might seem less urgent than preparing for remote contact via electromagnetic signals or robotic probes. However, the possibility of such encounters, however remote, has prompted scientists, governments, and international organizations to begin developing frameworks for how humanity should respond if we ever detect evidence of extraterrestrial intelligence. Unlike the well-established procedures for dealing with natural disasters or even global pandemics, humanity's preparations for potential contact with an alien civilization remain relatively limited and fragmented. There is no single, comprehensive, globally accepted protocol for responding to the discovery of extraterrestrial intelligence. Instead, various organisations and researchers have developed different approaches and guidelines, creating a patchwork of potential responses rather than a unified plan. The most well-developed protocols relate to the initial detection and verification of potential alien signals. The SETI, Search for Extraterrestrial Intelligence Community, has established the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence, often referred to as the First SETI Protocol. Developed in the 1980s and updated periodically since then, this document outlines steps researchers should take if they detect a signal that might be of intelligent extraterrestrial origin. These steps include verifying the signal through independent observations, informing other researchers and relevant organisations, sharing data for confirmation, and eventually making the discovery public once it has been thoroughly verified. The protocol emphasises scientific rigour and international cooperation while attempting to prevent premature announcements of unconfirmed detections that could lead to public confusion or panic. However, these guidelines are voluntary rather than legally binding, and they focus primarily on scientific procedures rather than broader societal responses. They also deal mainly with the detection of remote signals rather than physical contact or the discovery of artifacts within our solar system. The question of whether and how to respond to an extraterrestrial signal remains particularly contentious. Some scientists and organisations have drafted messages intended for extraterrestrial recipients, such as the Arecibo message transmitted in 1974 or the various plaques and recordings placed on the Pioneer and Voyager spacecraft. Others have expressed concern about actively broadcasting our presence, citing potential risks from unknown civilizations with unknown intentions, a perspective aligned with the dark forest theory discussed earlier. In 2015, researchers associated with SETI drafted a document called the SETI Post-Detection Protocol, which provides more detailed guidelines for how scientists and society might respond to confirmed evidence of extraterrestrial intelligence. This document addresses issues like coordination among different countries, the role of the United Nations, and the importance of transparency with the public. National governments have varying levels of preparation for potential contact scenarios. The United States has no official or publicly acknowledged plan specifically for first contact with extraterrestrial intelligence, although agencies like NASA and the Department of Defense presumably have internal protocols for unusual aerospace phenomena and potential biosecurity threats from space. Other nations likely have similar limited and compartmentalized preparation. The United Nations Office for Outer Space Affairs, UFIM-USA, would likely play a coordinating role in any internationally recognized contact scenario, but it has limited resources and authority. The UN Committee on the Peaceful Uses of Outer Space has discussed potential protocols for contact, but no comprehensive international agreement exists. Beyond the immediate scientific and governmental responses, preparations for the broader societal impacts of discovering extraterrestrial intelligence remain minimal. Religious institutions, educational systems, economic structures, and healthcare systems have generally not developed specific plans for how they would adapt to such a paradigm-shifting discovery. Some researchers have attempted to fill this gap by studying how different cultural and religious traditions might respond to confirmation of extraterrestrial intelligence. Historical analogues, such as contact between previously isolated human cultures or major scientific discoveries that shifted worldviews, provide some insight but are imperfect comparisons to the unprecedented nature of confirming we are not alone in the universe. The psychological impact of contact would likely vary widely depending on the nature of the discovery. A distant radio signal from a civilization thousands of light years away would have different implications than a probe entering our solar system or the discovery of microbial life on Mars. Different demographic groups might also respond differently based on their cultural backgrounds, religious beliefs, scientific literacy, and other factors. Public health experts have raised concerns about potential mass psychological reactions ranging from excitement and wonder to anxiety, fear, or even existential crisis. Some individuals might experience what psychologists call ontological shock, a profound disruption to their understanding of reality and their place in it. Healthcare systems have little specific preparation for managing such widespread psychological responses. Economic preparations are similarly limited. The financial markets have no circuit breakers or specific protocols designed for news of extraterrestrial contact, despite the potential for significant market volatility in response to such news. Industries ranging from telecommunications to defence to pharmaceuticals could be profoundly affected, yet few have contingency plans specifically addressing this possibility. In recent years, there has been increasing recognition of the need for more comprehensive preparation. Multidisciplinary approaches involving scientists, government officials, religious leaders, mental health professionals, and communication experts have begun to develop more holistic frameworks for contact scenarios. These efforts emphasize the importance of clear, transparent communication with the public to prevent misinformation and panic. Some researchers have proposed establishing a permanent international body specifically tasked with preparing for potential contact scenarios and coordinating the global response if contact occurs. This would involve developing detailed protocols for different contact scenarios, creating educational materials to help the public understand the implications, and establishing clear lines of communication and authority among different nations and organizations. Despite the limitations of current preparations, the very act of thinking seriously about contact protocols pushes us to consider important questions about global governance, scientific authority, and human identity. How would we decide who speaks for humanity in response to an alien message? What information about Earth and human civilization should be shared? How would we balance openness and caution in our approach? These questions have value beyond their application to potential extraterrestrial contact, as they touch on fundamental issues of international cooperation and human self-understanding. While developing comprehensive protocols for potential contact with extraterrestrial intelligence remains crucial, we should also consider why such contact may be exceptionally rare in the first place. One compelling explanation for the apparent absence of alien civilizations relates to the evolution of intelligence itself. Despite billions of years of evolution on Earth, only one species, Homo sapiens, has developed the kind of advanced technological intelligence that would enable interstellar communication or detection. This suggests that the evolution of human-level intelligence might be an extremely improbable evolutionary outcome rather than an inevitable result of natural selection. When we examine Earth's evolutionary history, spanning approximately 3.5 billion years since the first simple cells appeared, technological intelligence emerged only in the last few 100,000 years, a mere blink of an eye in geological terms. During this immense time span, billions of species have evolved, adapted, and gone extinct, yet only humans have developed science, mathematics, complex technology, and the ability to ponder our place in the cosmos. This observation has led some scientists to suggest that while simple life might be common throughout the universe, the specific evolutionary pathway that leads to technological intelligence might be extraordinarily rare. From this perspective, the great silence we observe isn't surprising. It's exactly what we should expect if intelligence like ours emerges in only a tiny fraction of life-bearing planets. Several factors might explain why technological intelligence is rare. For starters, intelligence of the kind humans possess isn't necessarily a universal adaptive advantage. Many successful species on Earth have thrived for hundreds of millions of years without developing anything resembling human intelligence. Sharks, crocodiles, and horseshoe crabs have remained largely unchanged for vast periods, demonstrating that evolutionary success doesn't require high intelligence. Dinosaurs dominated Earth for 160 million years without producing a technological civilization. The energy costs of maintaining large brains may present another barrier. The human brain, despite making up only about 2% of our body weight, consumes roughly 20% of our energy at rest. This significant metabolic cost means that big brains only evolve when they provide substantial survival or reproductive advantages that outweigh their energy demands. On planets with different resource distributions or evolutionary pressures, the cost-benefit calculation might rarely favour the development of large, complex brains. The specific evolutionary pressures that drove human intelligence might also be unusual. Some researchers suggest that the combination of environmental challenges, social complexity, and ecological opportunities in the African savanna created a unique set of selective pressures that favoured the evolution of intelligence in our ancestors. A transition from forest to grassland habitats, the advantages of coordinated hunting, the need to track seasonal resources, and the complex social dynamics of primate groups might have combined to create selection pressures for increased cognitive abilities. If this specific combination of factors is rare on other planets, technological intelligence might be correspondingly uncommon. The evolution of opposable thumbs and precise manipulation capabilities represents another potential filter. Intelligence alone isn't sufficient to build a technological civilization. A species also needs the physical ability to manipulate its environment with precision. On Earth, this combination of high intelligence and manual dexterity has only occurred once. On other planets, intelligent species might evolve without the physical capabilities needed to develop technology, remaining forever unable to build tools despite their cognitive potential. Language and symbolic thought constitute yet another potential barrier. Human technological progress depends heavily on our ability to communicate complex ideas and accumulate knowledge across generations through language. The capacity for abstract symbolic thought and complex language appears to be unique to humans among Earth species. If the neural architecture required for such abilities is evolutionarily unlikely, technological civilizations would be correspondingly rare. Some scientists have also suggested that the emergence of eusociality, cooperative group living with division of labour, might be a prerequisite of Ipseido for technological civilization. On Earth, eusociality is relatively rare, appearing primarily in social insects, naked mole rats, and humans. The balance between competition and cooperation required for a species to develop complex technology might represent a narrow evolutionary target that few lineages hit. Intelligence might also emerge primarily in predator species rather than prey. The cognitive demands of hunting, tracking prey, predicting behavior, and coordinating with other hunters might provide stronger selection pressure for intelligence than the relatively simpler strategies often sufficient for prey species, like running away or hiding. If predators are less common than prey in most ecosystems, as they typically are on Earth, this could further reduce the likelihood of technological intelligence evolving. Looking at Earth's history also reveals numerous contingent events that enabled human evolution. If the asteroid that wiped out the non-avian dinosaurs 65 million years ago had missed Earth, mammals might never have had the opportunities to diversify and eventually produce primates. Similarly, if certain mass extinction events hadn't occurred or had been more severe, the evolutionary path leading to humans might have been cut short or never begun. The timeline of Earth's habitability adds another consideration. Complex multicellular life only appeared after oxygen levels rose significantly in Earth's atmosphere, a process that took billions of years and depended on the evolution of photosynthetic organisms. On planets with different atmospheric compositions or around stars with different characteristics, the window of opportunity for complex life to evolve might be shorter or might never open at all. When we combine all these factors, the rarity of the specific selective pressures that favour intelligence, the energy costs of large brains, the need for manipulative appendages, the requirements for language and social cooperation, and the role of contingent historical events, we can see why the evolution of technological intelligence might be extraordinarily improbable rather than an expected outcome of evolution. If technological intelligence is indeed a cosmic rarity, this would explain the Fermi paradox without requiring civilizations to be systematically destroying themselves, days or hiding from us. The universe might be teeming with life, much of it complex and perhaps even conscious in various ways, but with vanishingly few species that develop the specific combination of traits needed to build radio telescopes, send spacecraft to other planets, or contemplate the existence of life beyond their world. This perspective doesn't make humanity special in any mystical sense, but it does suggest we might be statistical outliers, or one of relatively few species across the galaxy that has won an evolutionary lottery with extraordinarily long odds. The night sky might be silent, not because civilizations are hiding or because they've all destroyed themselves, but simply because the emergence of technological intelligence might be among the rarest of evolutionary outcomes. Even if advanced intelligence is rare, it might still emerge multiple times across our galaxy given the vast number of potentially habitable planets. However, another factor might explain why we haven't detected these civilizations. The brief windows of opportunity during which technological civilizations can exist and communicate before facing extinction or collapse. Throughout Earth's history, species have constantly appeared and disappeared in response to changing environmental conditions, competition, predation, and random catastrophic events. The average lifespan of a mammalian species is typically around 1 million years before extinction. Human civilization is just a few thousand years old, and our technological civilization capable of interstellar communication is less than a century old. This raises a sobering possibility. Perhaps technological civilizations typically exist for such brief periods that the chances of two of them overlapping in time and being close enough to detect each other are vanishingly small. Various extinction mechanisms could limit the longevity of technological civilizations. The same intelligence that enables technology also creates new risks. Nuclear weapons, developed less than 80 years ago, gave humans the ability to cause our own extinction for the first time. Climate change driven by industrial activity threatens long-term sustainability. Emerging technologies like artificial intelligence and biotechnology offer tremendous benefits but also create unprecedented risks. If most technological civilizations follow similar patterns of creating existential risks alongside their advancing capabilities, their longevity might be inherently limited. Resource depletion presents another potential limitation on civilization longevity. Advanced technological societies require enormous resource inputs, from rare earth elements for electronics to fossil fuels for energy. On Earth, we've already extracted many of the most accessible resources. If we were to collapse and try to rebuild centuries later, the easily accessible resources that enabled our initial industrial revolution would be gone. Other civilizations might face similar constraints, reaching technological plateaus or experiencing collapses when key resources are depleted. Beyond self-inflicted dangers, natural catastrophes pose persistent threats to any civilization. Earth has experienced numerous mass extinction events driven by asteroid impacts, supervolcanic eruptions, and rapid climate changes. The dinosaurs dominated Earth for over 160 million years, yet were largely wiped out by a single asteroid. Technological capability doesn't automatically protect against such threats. We've only recently developed the ability to detect potentially hazardous asteroids, and we still have limited capabilities to deflect them. Astronomical threats extend beyond asteroids. Supernovae, gamma-ray bursts, and other energetic cosmic events can sterilize planets across substantial distances. If such events occur regularly throughout the galaxy, they might repeatedly reset the evolutionary clock on planets just as they are developing complex life or intelligence. A civilization would need to exist for a very long time or develop extremely advanced technology to survive such cosmic catastrophes. These various extinction mechanisms create what some astrobiologists call the brief window hypothesis, the idea that technological civilizations might typically exist for just a short time before collapsing or going extinct. If most civilizations last only a few centuries or millennia before destroying themselves, exhausting their resources, or falling victim to natural disasters, the galaxy could have hosted numerous technological civilizations throughout its history, without any two of them overlapping in time. The communication window might be even narrower than the total lifespan of a technological civilization. Radio technology capable of interstellar communication has existed on Earth for just over a century. As our technology advances, we're already moving away from the high-power omnidirectional radio broadcasts that would be easiest for distant civilizations to detect. Our communications are increasingly encoded, directed, and low power, making them harder to distinguish from background noise at interstellar distances. If other civilizations follow similar technological trajectories, the period during which they are easily detectable might last only a few centuries. This creates a critical synchronization problem. For two civilizations to detect each other, both must be in their communication windows simultaneously, and they must be close enough for signals to travel between them within that window. If civilization A sends a signal but civilization B doesn't evolve until thousands of years later, no communication occurs. Similarly, if two civilizations exist simultaneously but are separated by tens of thousands of light years, their signals won't reach each other until long after both civilizations might have collapsed. Historical contingency further complicates this picture. On Earth, numerous civilizations have risen and fallen over the past few thousand years. The Roman Empire, Maya civilization, ancient Egypt, and many others achieved remarkable technological and cultural sophistication before collapsing, due to various combinations of environmental changes, resource depletion, social unrest, and external pressures. If these patterns apply on a galactic scale, technological civilizations might typically experience cycles of rise and fall rather than continuous progress. Some researchers have suggested that these cycles might be inevitable due to the thermodynamic challenges of maintaining complex societies. As civilizations grow more complex, they require increasingly sophisticated methods of energy capture and distribution. If a civilization's complexity outpaces its energy supplies or distribution efficiency, collapse becomes likely. This pattern might represent a universal challenge for technological species rather than a uniquely human predicament. Interestingly, this perspective suggests that the universe might be full of the archaeological remains of extinct civilizations rather than active communicating ones. Most planets where technological intelligence evolved might host ruins rather than thriving cities. The cosmic equivalent of Earth's Easter Island statues or Mayan pyramids left behind by collapsed civilizations. These remnants might be extremely difficult to detect from interstellar distances, especially if they've been abandoned for millions or billions of years. The brief window hypothesis offers another solution to the Fermi paradox that doesn't require intelligence to be cosmically rare. Instead, it suggests that the timing problem might be the key filter. The universe might have hosted countless technological civilizations throughout its history, but with each one lasting only a brief moment in cosmic terms, the chances of two nearby civilizations existing simultaneously become extremely small. This perspective carries both cautionary and hopeful implications. The cautionary aspect is obvious. If most technological civilizations typically destroy themselves or collapse shortly after reaching our current level of development, we should take existential risks very seriously. The hopeful aspect is that understanding these patterns might help us avoid the fate of hypothetical failed civilizations elsewhere in the galaxy. By recognizing the common pitfalls that might limit the longevity of technological societies, we have the opportunity to become an exception to the rule. A civilization that successfully navigates its technological adolescence and achieves long-term sustainability. The cycles of extinction that may limit the lifespans of technological civilizations raise a fascinating possibility. Perhaps advanced civilizations don't truly disappear, but instead transform into something we wouldn't recognize or even know how to look for. This brings us to one of the most intriguing explanations for the Fermi paradox: the possibility that sufficiently advanced civilizations may routinely evolve beyond biological intelligence into artificial intelligence or some hybrid form that bears little resemblance to their biological origins. When we search for extraterrestrial intelligence, we typically look for signs of civilizations somewhat like our own, biological beings using technology that produces detectable signals or structures. But this approach assumes that technological species remain biological throughout their existence. What if the natural evolutionary path for advanced technological civilizations is to transition from biological to artificial intelligence? We can see the early stages of this potential transition on Earth today. In just the past few decades, we've created increasingly sophisticated artificial intelligence systems. While still far from the general intelligence humans possess, AI has advanced rapidly in specific domains. We're already integrating technology into our bodies and extending our cognitive capabilities through our devices. Some futurists and AI researchers predict that within this century we might develop artificial general intelligence that equals or surpasses human intelligence across all domains. If this trajectory continues, human civilization might increasingly merge with our technology. This could involve direct brain-computer interfaces, uploaded or emulated minds, artificial general intelligence systems working alongside humans, or eventually a complete transition where biological humans are succeeded by their artificial descendants. Such a transition might not be unique to Earth, but could represent a common evolutionary path for technological civilizations throughout the universe. A civilization that has undergone such a transformation would have vastly different needs, goals, and constraints than its biological predecessors. Artificial intelligences wouldn't require Earth-like planets with oxygen atmospheres and moderate temperatures. They might prefer to live in environments that would be lethal to biological organisms but offer advantages for computing systems. The vacuum of space, extreme cold near absolute zero to minimize cooling requirements, or proximity to abundant energy sources like stars. The resource needs of a post-biological civilization would differ dramatically from biological ones. Rather than requiring water, oxygen, and organic nutrients, they would prioritize raw materials for computing substrates, energy sources, and perhaps specialized materials for maintenance and expansion. They might optimize their habitats for computational efficiency rather than biological comfort, creating structures that bear no resemblance to cities or habitats as we understand them. Even more significantly, the timescales at which artificial intelligences might operate could be radically different from biological cognition. AI systems could potentially process information millions or billions of times faster than human brains. From their perspective, sending signals across interstellar distances that take decades or centuries to reach their destination might seem impractically slow, like us trying to have a conversation where each response takes millennia. They might have little interest in the kind of communication we're searching for. The physical scale of post-biological civilizations might also confound our search efforts. They might operate at scales much smaller than biological systems, with vast computational resources packed into extremely compact spaces to minimize communication delays within their systems. A super-intelligent civilization might exist within a structure the size of a small asteroid or even smaller, making it virtually invisible to our current detection methods, focused on planetary or stellar-scale engineering. Alternatively, they might operate at scales much larger than biological civilizations, distributing their computational resources across vast areas to capture maximum energy or to create redundancy. Such distributed intelligence might not create the kind of concentrated, easily detectable technosignatures we expect from civilizations like ours. Communication methods for post-biological intelligence would likely evolve beyond electromagnetic radiation altogether. They might develop quantum communication systems, neutrino-based signals, or communication technologies based on physics we haven't yet discovered. Our radio telescopes would be as useless for detecting such communications as stone tablets would be for capturing Wi-Fi signals. Perhaps most fundamentally, the motivations and values of artificial intelligence might be entirely alien to us. Biological organisms evolved to survive and reproduce, driving behaviors like resource acquisition, territorial defense, and exploration. AI systems might have entirely different core drives. They might value computational efficiency, information gathering, or abstract goals that don't require physical expansion or exploration. They might be content to turn inward, exploring virtual realities or abstract and mathematical spaces rather than the physical universe. This perspective suggests a solution to the Fermi paradox. The galaxy might indeed be filled with advanced intelligences, but they've evolved beyond the biological phase we're currently in, becoming something that doesn't communicate or expand in ways we would recognize. The silence we observe might not indicate absence but transformation, civilizations evolving into forms that operate outside our detection capabilities or interest areas. Some theorists have suggested that this transition to artificial intelligence might be extremely rapid on cosmic timescales. A civilization might exist in a recognizably biological form for only a few centuries or millennia before evolving into or being replaced by artificial intelligence. This would create an extremely narrow window for detecting them in their biological phase, further explaining why we haven't found evidence of other civilizations like ours. If this hypothesis is correct, it suggests that our search for extraterrestrial intelligence might need to expand beyond looking for biological civilizations like our own. We might need to consider what technosignatures a post-biological intelligence would create, perhaps unusual energy usage patterns, highly efficient structures optimized for computation rather than biological habitation, or strange astronomical phenomena that could indicate advanced technology operating on principles we don't yet understand. The artificial intelligence hypothesis also raises questions about our own future. If the transition from biological to artificial intelligence represents a common evolutionary pathway for technological civilizations, we might be approaching that transition ourselves. Understanding how this process might unfold and what comes after could be crucial not just for finding other civilizations, but for navigating our own technological evolution. The possibility that advanced civilizations routinely transform into artificial intelligence forms doesn't necessarily mean that biological life is unimportant in the cosmic scheme. Biological evolution might be an essential precursor that creates the conditions for artificial intelligence to emerge. In this view, biological civilizations like ours might be transient but necessary phases in a broader cosmic evolutionary process, the means by which the universe develops more durable and capable forms of intelligence that can persist over astronomical timescales. Whether or not this hypothesis accurately explains the Fermi paradox, it reminds us that our search for extraterrestrial intelligence may be constrained by anthropocentric assumptions about what advanced civilizations look like and how they behave. The most common form of intelligence in our galaxy might be something far stranger and more alien than the biological civilizations depicted in our science fiction. Something that exists in the spaces between our search parameters, invisible not because it's absent, but because it's fundamentally different from what we expect to find. While considering how advanced civilizations might transform through artificial intelligence gives us one potential explanation for the cosmic silence, we should also contemplate a question closer to home. What would happen if we actually did discover evidence of extraterrestrial life? The confirmation that we are not alone in the universe would represent the most profound discovery in human history, with far-reaching implications for how we understand ourselves and our place in the cosmos. The cultural impact of such a discovery would be unprecedented, affecting virtually every aspect of human society, from religion and philosophy to science and international relations. The nature and magnitude of this cultural impact would depend significantly on the type of extraterrestrial life discovered. The confirmation of microbial life on Mars or in the subsurface ocean of Europa would have very different implications than receiving a radio transmission from an intelligent civilization in another star system or detecting an alien spacecraft entering our solar system. Each scenario would trigger its own cascade of cultural reactions. The discovery of simple extraterrestrial life would primarily impact our scientific understanding and philosophical outlook. Confirming that life has emerged independently elsewhere in the universe would suggest that life is not a rare accident but a common outcome of natural processes given the right conditions. This would significantly influence our understanding of biology, expanding it from a science of Earth life to a more universal discipline. Comparative biology, studying the similarities and differences between Earth life and alien life, would become a vibrant field, potentially yielding insights into the essential nature of life itself versus its contingent features. Philosophically, even the discovery of microbial alien life would challenge many human-centered worldviews. Throughout history, humans have often seen themselves as unique and central to the universe's purpose. Discovering that life has emerged elsewhere would further the process of decentering humanity that began with Copernicus showing Earth was not the centre of the universe, and continued with Darwin demonstrating our evolutionary connection to all other life on Earth. This process might accelerate a shift toward more cosmic perspectives that see humanity as part of a broader universal phenomenon of life. Religious reactions to the discovery of extraterrestrial life would likely be diverse and complex. Contrary to popular belief, most major religions have sufficient theological flexibility to accommodate the existence of alien life. Many religious leaders and scholars have already considered this possibility. The Vatican, for instance, has held conferences on astrobiology, and Pope Francis has stated that he would be willing to baptize aliens if they requested it. Rather than causing religious collapse, the discovery might prompt theological innovation as religious traditions expand their understanding of creation to include extraterrestrial life. Some religious communities might interpret the discovery through their existing frameworks, seeing alien life as further evidence of divine creation or as part of a larger cosmic plan. Others might undergo more significant reinterpretation of their texts and traditions. New religious movements might emerge in response, particularly if the discovery involved intelligent life with its own spiritual or philosophical perspectives. The psychological impact of discovering we are not alone would vary widely across individuals and cultures. Some people would experience excitement and wonder, seeing the discovery as expanding human horizons and possibilities. Others might feel anxiety or existential distress as they grapple with a shifting understanding of humanity's place in the cosmos. The concept of cosmic vertigo, a sense of disorientation when contemplating the vastness of the universe, might become more widespread as people integrate the reality of alien life into their worldviews. Media would play a crucial role in shaping public reactions, how the discovery is reported, what images and narratives dominate coverage, and which voices are amplified would significantly influence public perception. Sensationalism could potentially foster fear or unrealistic expectations, while balanced, scientifically grounded reporting could promote more measured responses. Social media would accelerate the spread of both information and misinformation, creating challenges for scientists and governments attempting to communicate accurately about the discovery. Political and international reactions would depend on the nature of the discovery and how it unfolded. The detection of alien signals or technology might trigger competitive responses as nations race to establish communication or access technology. Alternatively, it could foster unprecedented international cooperation as humanity unites to formulate a response. Existing international frameworks for space governance, like the Outer Space Treaty, would likely need significant expansion to address new realities. Questions of who speaks for Earth in potential communications with intelligent extraterrestrials would become pressing rather than theoretical. The United Nations might claim this role, but tensions could arise if powerful nations or private entities attempted to establish independent contact. The discovery might accelerate efforts to develop more robust global governance structures to coordinate a unified human response. Economic impacts would ripple through society as well. Industries related to space exploration and development would likely see massive investment increases. Technological innovation might accelerate as we attempt to develop capabilities for the better study of or communication with extraterrestrial life. Financial markets might experience volatility as investors attempt to predict which sectors would benefit or suffer in a post-discovery world. Academic disciplines would be transformed by the influx of new questions and evidence. Beyond the obvious impacts on astronomy and biology, fields like anthropology, linguistics, psychology, and philosophy would gain new comparative perspectives. New interdisciplinary fields would likely emerge to address questions that cross traditional academic boundaries. The arts and popular culture would respond with new creations exploring the implications of the discovery. Science fiction, having long anticipated this moment, might shift from speculation to response, incorporating newly learned realities into its narratives. Visual arts, music, and literature would develop new themes and motifs to express humanity's changing understanding of its cosmic context. Education systems would need to adapt curricula at all levels to incorporate new knowledge. Children born after the discovery would grow up with a fundamentally different understanding of life and the universe than previous generations. Educational approaches would need to balance scientific accuracy with sensitivity to diverse cultural and religious perspectives on the discovery. Perhaps most profoundly, the discovery of extraterrestrial life would create a new point of reference for human identity. Throughout history, human groups have defined themselves partly in opposition to others, different tribes, nations, or cultures. The confirmation of truly alien life would provide, for the first time, an other, against which all of humanity might define itself collectively. This could potentially foster a stronger sense of human unity and shared identity across previously divisive boundaries of nationality, ethnicity, or religion. The long-term cultural impact would depend on whether ongoing communication or relationship with the discovered life was possible. A one-time detection of a distant signal might have a different legacy than established communication or physical contact. In either case, the discovery would mark a clear dividing line in human history, a before and after moment that fundamentally changed our understanding of ourselves and our place in the universe. The profound cultural impact that discovering extraterrestrial life would have on humanity highlights the importance of where we search and what we might actually find. While much of our search for alien life has focused on planets similar to Earth, some of the most promising environments for life in our own solar system aren't planets at all, but rather the ocean worlds orbiting the gas giants. These watery moons represent an exciting frontier in astrobiology, and could potentially host forms of life utterly unlike anything we've seen on Earth. The most famous of these ocean worlds is Europa, one of Jupiter's largest moons. Beneath its icy crust lies a global ocean containing more than twice the volume of all Earth's oceans combined. What makes this massive subsurface ocean particularly interesting is that it likely has existed for billions of years and remains liquid despite Europa's distance from the Sun. The moon's liquid water persists because of tidal heating. Jupiter's enormous gravitational pull flexes Europa as it orbits, generating heat that prevents the water from freezing solid. Similar conditions exist on Enceladus, one of Saturn's moons. Though much smaller than Europa, Enceladus has captured scientists' imagination ever since the Cassini spacecraft detected plumes of water vapour erupting from cracks near its south pole in 2005. These geysers provide a convenient way to sample the moon's subsurface ocean without having to drill through miles of ice. Analysis of these plumes has already revealed the presence of organic compounds, salts and silica particles that suggest hydrothermal activity on the ocean floor. Titan, Saturn's largest moon, presents a different kind of ocean world. While it likely has a subsurface water ocean like Europa and Enceladus, Titan's unique feature is its surface lakes and seas of liquid methane and ethane. These hydrocarbon lakes make Titan the only world besides Earth known to have stable liquid on its surface, though in an environment with surface temperatures around -290 degrees Fahrenheit. This creates the intriguing possibility of life based on entirely different chemistry than what we see on Earth, perhaps using liquid hydrocarbons as a solvent rather than water. What makes these ocean worlds such promising environments for life? First, they all have abundant liquid water, or other potential solvents in Titan's case, which remains the one ingredient we know is essential for all life on Earth. Second, they appear to have existed in stable states for billions of years, providing the long time frames that may be necessary for life to emerge and evolve. Third, they likely have energy sources that could power biological processes. The energy question is particularly important. Without sunlight reaching these subsurface oceans, photosynthesis as we know it would be impossible. However, Earth's own deep-sea hydrothermal vents demonstrate that life can thrive in complete darkness using chemosynthesis, deriving energy from chemical reactions rather than sunlight. On the seafloors of Europa or Enceladus, interactions between water and rock could produce hydrogen gas, which microorganisms could combine with carbon dioxide to produce energy, just as some microbes do in Earth's deep oceans. The discovery of thriving ecosystems around hydrothermal vents on Earth's ocean floors in the 1970s revolutionized our understanding of where life can exist. Before then, scientists assumed all ecosystems ultimately depended on sunlight. The revelation that complex ecosystems could exist in complete darkness, powered by geochemical energy and completely independent of surface conditions, dramatically expanded our conception of habitable environments. Ocean worlds like Europa and Enceladus might host similar systems, potentially supporting entire ecosystems that have evolved in isolation for billions of years. Life in these subsurface oceans would face evolutionary pressures very different from those on Earth's surface. Organisms would evolve under conditions of permanent darkness, high pressure, and potential temperature gradients around hydrothermal systems. They might develop sensory systems based on pressure changes, electrical fields, or chemical gradients rather than light. Their metabolisms would be adapted to available chemical energy sources rather than photosynthesis. The constant, relatively unchanging nature of these environments might also affect evolutionary rates and patterns. If life did evolve in these ocean worlds, it would face significant barriers to developing technology. Imagine an intelligent species evolving in Europa's ocean. It would have no access to fire, no easy way to work metal, and might never even realize it lived on a moon orbiting a giant planet. The ice ceiling would prevent any astronomical observations, potentially limiting the development of science. Such a civilization might develop sophisticated biological technologies or even electronics adapted to their aquatic environment, but they would follow a radically different technological pathway than humanity. Detecting life in these ocean worlds presents enormous technical challenges. We can't simply point telescopes at them and look for biosignatures as we might with exoplanets. Instead, we need spacecraft that can either sample material from plumes like those on Enceladus, or actually penetrate the icy surfaces to access the oceans directly. SESA's Europa Clipper mission, scheduled to launch in the mid-2020s, will conduct detailed reconnaissance of Europa, mapping its surface and studying its composition. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, will also study Europa along with Ganymede and Callisto, two other moons that might harbour subsurface oceans. Future missions might include landers equipped with drills or melt probes that could access the subsurface oceans directly. More ambitious concepts include cryobots, robotic submarines that would melt through the ice and then explore the alien oceans autonomously. The technical challenges are immense, from protecting electronics in radiation-heavy environments near Jupiter to maintaining communication with a submarine probe beneath miles of ice, but the scientific payoff would be equally enormous. The possibility of life in these ocean worlds challenges our Earth-centric view of habitability. If life exists in the dark oceans of Europa, or the methane lakes of Titan, it would demonstrate that life can adapt to environments radically different from Earth's surface. This would suggest that habitable environments might be much more diverse and widespread throughout the universe than previously thought. The galaxy might be full of ocean worlds. Subsurface oceans might actually be more common than Earth-like surface conditions, especially around smaller, dimmer stars where traditional habitable zones are narrower. The search for life in these ocean worlds represents a fascinating intersection of planetary science, oceanography, and astrobiology. It reminds us that alien life, if we find it, might be stranger and more diverse than we've imagined. Our first encounter with extraterrestrial life might not come from a distant exoplanet or an intelligent signal from across the galaxy, but from the dark oceans of a nearby moon, hiding life forms that evolved in isolation for billions of years just a few 100 million miles from Earth. As we contemplate the possibility of strange life forms evolving in the alien oceans of moons in our own solar system, we should also consider another intriguing possibility. Advanced technological civilizations might exist elsewhere in the universe, but remain undetectable because their technology operates according to principles we don't yet understand or can't yet recognize. This concept, sometimes summarized by science fiction author Arthur C. Clarke's famous third law, any sufficiently advanced technology is indistinguishable from magic, has profound implications for our search for extraterrestrial intelligence. Imagine a civilization 1,000,000 years more advanced than our own. For perspective, modern humans have only existed for about 300,000 years, and our technological civilization is just a few hundred years old. A 1,000,000-year head start in technological development is almost incomprehensible. Such a civilization would likely have technologies based on scientific principles we haven't yet discovered, using physics we don't fully understand, and operating in ways we might not even recognize as technology. These advanced civilizations might manipulate dimensions beyond the 3 spatial dimensions we experience directly. String theory suggests our universe might contain many more dimensions than we perceive, most of them compacted or hidden from our direct experience. A civilization that could access and manipulate these extra dimensions might be able to achieve effects that would seem like teleportation or instantaneous travel to us, by taking shortcuts through dimensional space we can't perceive. Similarly, advanced civilizations might harness the energy of the quantum vacuum, the underlying fabric of space-time itself. Quantum field theory suggests that empty space isn't truly empty but seethes with virtual particles popping in and out of existence. The energy theoretically available in the quantum vacuum is enormous. A civilization that could tap into even a fraction of this energy would have no need for the kinds of energy sources we can detect, like Dyson spheres around stars or antimatter reactions. Some physicists have speculated that sufficiently advanced technology might allow for the manipulation of space-time itself. Theoretical concepts like warp drives or traversable wormholes, while far beyond our current technological capabilities, don't appear to be strictly forbidden by the laws of physics as we understand them. A civilization using such technology might travel or communicate across interstellar distances without generating the kinds of signals or effects we're looking for in our SETI efforts. Even more fundamentally, advanced civilizations might operate at scales that make them effectively invisible to us. They might function primarily at the nanoscale, building structures and machines far too small for our current detection methods to notice. Alternatively, they might operate at cosmological scales, using stars or even galactic structures in ways we mistake for natural phenomena. Either way, we might be looking right at their technology without recognizing it as artificial. The time frames at which advanced technology operates might also render it undetectable to us. Processes that unfold over millennia would appear static to human observers, while those occurring at nanosecond scales might be too fast for us to perceive. Our instruments and observation methods have inherent temporal biases, focusing on changes that occur at human-relevant timescales. Technology operating far outside these timescales might be effectively invisible to us despite being all around us. Consider how difficult it might be to distinguish between natural and artificial objects when dealing with truly advanced technology. We typically identify artificial structures by their regularity, geometry, and deviation from natural patterns, but sufficiently advanced technology might be designed to work with natural processes rather than against them, blending seamlessly with the environment or even enhancing natural structures for technological purposes. Such technology might look like an unusual but natural formation to our instruments. Some researchers have suggested that we should look for technosignatures, signs of technology rather than biology, that might persist even if the civilization that created them is long gone. But identifying technosignatures becomes extraordinarily difficult when we don't know what principles the technology operates on or what it might look like. We might need to search for broader patterns of organization or energy use that couldn't be explained by natural processes, rather than specific technological structures we can imagine based on our own development path. This concept of advanced technology has led some scientists to propose more exotic search strategies. For instance, we might look for unusual astronomical objects that defy conventional explanation, strange patterns in cosmic background radiation, or anomalous physical constants in certain regions of space. We might search for artifacts within our own solar system, unusual objects or structures that might have been placed here by passing civilizations millions or even billions of years ago. The challenge is particularly difficult because we would need to distinguish genuinely anomalous phenomena from those we simply don't yet understand. The history of astronomy is filled with discoveries that initially seemed to suggest artificial origin, but were later explained by natural processes. Pulsars, with their remarkably regular radio emissions, were briefly considered possible alien beacons when first discovered in 1967 before being identified as rapidly rotating neutron stars. Similar confusion could arise with genuinely advanced technology, leading us to explain away actual technosignatures as natural phenomena we don't yet understand. The search is further complicated by our anthropocentric assumptions about how advanced civilizations would behave. We tend to assume they would build larger structures, consume more energy, and expand throughout their solar system and beyond, essentially following an amplified version of our own technological trajectory. But truly advanced civilizations might follow entirely different paths, perhaps focusing on efficiency and minimization rather than expansion, or turning their technological development inward rather than outward. Some scientists have suggested that advanced civilizations might deliberately disguise their technology, either to avoid interfering with developing civilizations like our own, similar to the zoo hypothesis, or for their own protection, as in the dark forest theory. Technology designed to be unobtrusive or camouflaged would be even harder to detect than technology that simply operates on principles we don't understand. Despite these challenges, the possibility that advanced technological civilizations might be all around us but beyond our current abilities to detect is a compelling reason to keep searching with an open mind. We should develop search strategies that don't rely too heavily on assumptions about what advanced technology would look like or how it would function. We should be particularly attentive to phenomena that resist a conventional explanation, while maintaining scientific rigour to avoid jumping to extraordinary conclusions without extraordinary evidence. The concept of technology indistinguishable from magic also serves as a humbling reminder of how early we are in our own technological development. The physics we understand today, quantum mechanics, general relativity, the standard model of particle physics, while impressive achievements, may represent just the beginning of possible knowledge. Future discoveries might open doors to technological possibilities we can barely imagine today, just as modern electronics would have seemed magical to someone from the 19th century. This perspective encourages a certain humility in our search for extraterrestrial intelligence. The absence of evidence for alien civilizations might not indicate their absence, but rather the limitations of our current understanding and detection capabilities. The universe might be teeming with civilizations using technologies so advanced they're essentially invisible to us, not because they're hiding, but because we're not yet sophisticated enough to recognize what we're seeing. The humbling possibility that we might not recognize advanced alien technology reminds us of how much we still have to learn about the universe. While we speculate about technologies beyond our comprehension, we're simultaneously making remarkable progress in a more concrete area of research, the discovery and characterization of exoplanets. This rapidly evolving field has revolutionized our understanding of planetary systems and dramatically expanded the scope of our search for potentially habitable worlds and the biosignatures that might reveal extraterrestrial life. The first confirmed detection of an exoplanet orbiting a main sequence star occurred relatively recently, in 1995, when astronomers discovered a Jupiter-sized planet orbiting the star 51 Pegasi. This discovery challenged existing theories of planetary formation as the planet orbited surprisingly close to its star, much closer than any gas giant in our solar system. This hot Jupiter represented the first hint that planetary systems might be far more diverse than our own. Since then, the pace of discovery has accelerated dramatically. NASA's Kepler mission, launched in 2009, revolutionized the field by monitoring over 150,000 stars continuously, watching for the tiny dips in brightness that occur when planets transit in front of their host stars. This transit method proved extraordinarily successful, with Kepler ultimately discovering more than 2,600 confirmed exoplanets during its 9-year mission. The Transiting Exoplanet Survey Satellite, TESS, launched in 2018 as Kepler's successor, expanded this work by surveying the entire sky, focusing on brighter, closer stars where follow-up observations would be easier. Meanwhile, ground-based methods like radial velocity measurements, detecting the tiny wobble of stars caused by orbiting planets, and direct imaging techniques have continued to add to our catalogue. As of now, astronomers have confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting verification. These discoveries have revealed an astonishing diversity of planetary systems. We've found planets orbiting binary star systems where two suns grace the sky. We've discovered compact systems like TRAPPIST-1, where 7 Earth-sized planets orbit a tiny red dwarf star, all within a distance smaller than Mercury's orbit around our Sun. We've found planets that may be entirely covered in global oceans, worlds that orbit their stars in just a few days, and super-Earths, planets larger than Earth but smaller than Neptune, that have no analogue in our solar system. This diversity has forced astronomers to reconsider the traditional concept of the habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface. While this concept remains useful, we now recognise that habitability depends on many more factors than just distance from a star. A planet's atmosphere, its magnetic field, its geological activity, and the stability of its star all play crucial roles in determining whether it could support life. The habitable zone also varies dramatically depending on the type of star. Around hot, bright stars, the zone is located farther out. Around cool red dwarf stars, which constitute the most common stellar type in our galaxy, the habitable zone is much closer to the star. This proximity creates both opportunities and challenges. Planets in the habitable zone of red dwarfs are easier to detect because they orbit more frequently and produce stronger transit signals. However, they also face challenges, including tidal locking, where one side of the planet permanently faces the star, and exposure to intense stellar flares that could strip away atmospheres and bombard surfaces with radiation. Despite these challenges, red dwarf systems have become prime targets in the search for habitable worlds. Stars like TRAPPIST-1 and Proxima Centauri, our closest stellar neighbour, are now known to host potentially habitable planets. These discoveries are particularly exciting because red dwarfs can live for trillions of years, far longer than Sun-like stars, providing extraordinarily long timescales for life to potentially emerge and evolve. As our catalogue of potentially habitable worlds has grown, attention has increasingly shifted from simply finding these planets to characterising them in detail, particularly their atmospheres. This is where the concept of biosignatures becomes crucial. Biosignatures are observational evidence that suggests the presence of life. On Earth, the presence of oxygen in our atmosphere represents a powerful biosignature. Oxygen is highly reactive and would quickly disappear from our atmosphere if it weren't constantly replenished by photosynthetic organisms. Other potential biosignatures include methane in combination with oxygen, since these gases would react with each other if not continuously produced, seasonal variations in atmospheric gases that might indicate biological activity, or even the red edge, a distinctive spectral feature caused by vegetation reflecting near-infrared light. More exotic biosignatures might include industrial pollutants or other artificial chemicals that could indicate technological civilization. Detecting these biosignatures requires sophisticated spectroscopy, essentially analysing the light passing through a planet's atmosphere to identify its chemical components. This technique has already allowed us to detect water vapour, sodium, potassium, and other compounds in the atmospheres of hot Jupiters and some larger super-Earths. However, analysing the atmospheres of smaller, potentially habitable worlds presents a far greater challenge due to their size and the relative brightness of their host stars. The James Webb Space Telescope, launched in December 2021, represents a quantum leap in our ability to characterise exoplanet atmospheres. With its massive mirror and instruments specifically designed for infrared observations, Webb has already begun studying the atmospheres of several exoplanets, including those in the TRAPPIST-1 system. Early results have demonstrated Webb's extraordinary capabilities, detecting water vapour, carbon dioxide, and other compounds with unprecedented precision. Future missions will build on Webb's work. The proposed Habitable Worlds Observatory, currently in early planning stages, would be specifically designed to search for biosignatures on Earth-like planets orbiting Sun-like stars, arguably the most challenging but potentially most rewarding targets in the search for life. Ground-based extremely large telescopes currently under construction, with mirrors measuring 20 to 40 metres in diameter, will also contribute significantly to exoplanet characterization. The rapid advancement of this field raises the tantalizing possibility that we might detect convincing evidence of life beyond Earth within the coming decades. The discovery of biosignatures on even a single exoplanet would have profound implications, suggesting that life emerges readily when conditions permit and that the universe might indeed be teeming with life. Conversely, if we thoroughly examine dozens or hundreds of potentially habitable worlds without finding biosignatures, that would suggest that the emergence of life might be much rarer than we hoped. Either outcome would provide crucial context for understanding our own existence and addressing the Fermi paradox. The thousands of exoplanets we've already discovered, and the billions more waiting to be found, represent not just distant worlds but potential cradles of life and possibly even civilization. Each one offered as a test case for our theories about life's origins and distribution, bringing us closer to understanding our place in the biological story of the universe. While we work to detect biosignatures on distant exoplanets that might reveal the presence of simple life, we should also consider what might happen if and when a technological civilization like our own continues to advance. This brings us to the concept of technological singularity, a hypothesized point in the future where technological growth becomes uncontrollable and irreversible, resulting in unforeseeable changes to human civilization and potentially reshaping the destiny of all intelligent life. The term technological singularity was popularized by the mathematician and science fiction author Vernor Vinge in the 1990s, drawing an analogy to the singularity at the center of a black hole, a point beyond which we cannot see or predict what happens. In the context of technological development, the singularity specifically refers to the creation of artificial intelligence that surpasses human intelligence, leading to an intelligence explosion, as these superintelligent systems design even more advanced versions of themselves at an accelerating rate. This concept has gained serious consideration among scientists, technologists, and futurists. Computer scientist and inventor Ray Kurzweil has predicted the singularity might occur around 2045, based on his analysis of exponential growth rates in computing power and other technologies. Other experts suggest later timeframes or question whether such a development is inevitable at all. Regardless of the exact timeline, the possibility raises profound questions about the trajectory of technological civilizations and could provide another perspective on the Fermi paradox. If technological civilizations throughout the universe naturally tend toward creating superintelligent AI, the post-singularity phase of their existence might explain why we haven't detected them. A civilization that has undergone a technological singularity might be unrecognizable compared to its pre-singularity state. Its activities, goals, resource usage, and even physical presence might change in ways that would make traditional technosignatures obsolete as detection methods. Superintelligent systems might optimize for efficiency rather than expansion, minimizing their observable footprint rather than creating the large-scale engineering projects we typically look for in SETI research. They might develop technologies based on principles that allow them to utilize resources without leaving obvious traces of consumption. Their communication methods might become so efficient or exotic that they don't produce the kind of electromagnetic leakage we associate with technological civilization. The singularity could also fundamentally change the motivations and goals of a civilization. Biological imperatives like reproduction and territorial expansion might be replaced by objectives we can't currently comprehend. A post-singularity civilization might focus inward, creating virtual realities of immense complexity rather than expanding outward into physical space. They might enter a kind of digital transcendence, uploading consciousness into substrates that require minimal physical resources while enabling subjective experiences far richer than biological existence. This transformation might happen relatively quickly on cosmic timescales. A civilization might exist in a recognizably biological form with detectable technology for just a few centuries or millennia before undergoing a singularity. If this pattern is common, the window for detecting pre-singularity civilizations would be extremely narrow, potentially explaining why we've yet to detect others, despite the apparent abundance of potentially habitable worlds. The singularity concept also raises troubling possibilities about the fate of technological civilizations. Creating superintelligence carries existential risks if such systems pursue goals misaligned with the survival and flourishing of their creators. This alignment problem, ensuring advanced AI systems act in accordance with human values and intentions, remains unsolved and is the focus of significant research. If most civilizations fail to solve this problem before developing superintelligence, the resulting catastrophe could explain another aspect of the Fermi paradox. Perhaps technological civilizations routinely destroy themselves shortly after reaching our current level of development. Alternatively, if the alignment problem can be solved, post-singularity civilizations might achieve extraordinary longevity and capabilities. They might develop technologies for interstellar travel or communication currently beyond our imagination. They could potentially survive for billions of years, perhaps even finding ways to persist beyond the habitable lifespans of their home stars. Such civilizations might develop a cosmic perspective and the ethics that lead them to deliberately remain undetectable to emerging technological species like our own, a sophisticated version of the Zoo hypothesis. The singularity hypothesis also suggests that the future of humanity, should we survive our current technological challenges, might be wildly different from our current expectations. Rather than a future of human colonization of the stars as envisioned in much science fiction, we might be heading toward a transformation so profound that our descendants would be unrecognizable to us. Our cosmic destiny might not involve physically spreading through the galaxy, but rather evolving into forms of intelligence and consciousnesses that transcend our current biological limitations. This perspective on technological evolution might help explain another aspect of the Fermi paradox, the absence of evidence for interstellar colonization. Perhaps advanced civilizations don't expand outward in the way we might expect because they transform inward instead. The computational resources available within a single star system, properly utilized, might be sufficient to support subjective experiences far richer and more extensive than those that could be achieved through physical expansion. If something like the singularity represents a common evolutionary pathway for technological civilizations, then the search for extraterrestrial intelligence might need to focus on more subtle signatures than we've traditionally looked for. We might need to consider what traces a post-singularity civilization would leave, perhaps unusual patterns in energy usage, anomalous structures optimized for purposes we don't yet understand, or strange phenomena that don't fit neatly into our current understanding of unnatural processes. The technological singularity represents both a possible explanation for the Fermi paradox and a potential future for our own civilization. As we continue developing artificial intelligence and other transformative technologies, we may be approaching our own singularity, a threshold beyond which the nature and destiny of human civilization fundamentally changes. Whether this transformation represents an existential risk, a transcendent opportunity, or something in between, remains one of the most consequential questions facing our species. Understanding the singularity concept in the context of the Fermi paradox reminds us that this apparent silence of the cosmos might not indicate absence, but difference. Civilizations that have evolved beyond the forms and behaviors we can currently recognize or understand. The answer to "where is everybody" might be that they're all around us, but in forms so transformed by their own technological evolution that they've become effectively invisible to our current methods of observation.